Hello there, and welcome. Tonight I want to take you somewhere that exists between the edges of what we know and the vast territories of what we can only imagine. I want to take you to a place where the boundaries between the physical and the philosophical blur like stars seen through tired eyes, where the hard facts of astronomy meet the soft questions of consciousness, and where the universe itself might be something more than we've ever dared to consider. You're here now, perhaps lying in your bed, perhaps sitting in a comfortable chair, perhaps with earphones creating a small bubble of sound just for you. And in this moment, you and I are going to explore something together that sounds almost impossible to say out loud. Something that might make you smile at its strangeness, and yet something that might also make you wonder in ways you haven't wondered since you were very young, and the world was still full of mysteries that adults hadn't yet explained away. Before we begin this journey together, I wonder where you are right now, not just physically, but in time, in your day, in your life. Are you listening from a city where the lights never quite let the stars through? Or are you somewhere rural where the Milky Way still paints its ancient path across the darkness? What time is it where you are? Is it that precious hour just past midnight when the world feels like it belongs only to the wakeful few? Or is it earlier in the evening when the day's responsibilities are finally releasing their grip on your thoughts? I'd love to know, and if you feel like sharing in the comments below, please tell me where you're listening from, what brought you here tonight, what questions about the universe keep you awake or help you sleep. And if this journey we're about to take together brings you any measure of peace or wonder, perhaps you might consider subscribing, becoming part of this quiet community of night thinkers and cosmic wanderers who gather here when the world grows still and the big questions feel safe to ask. The question I want to explore with you tonight is this: what if space itself could feel pain? Now, I know how that sounds at first, perhaps absurd, perhaps impossible, perhaps like something from a science fiction story that takes too many liberties with physics. And you're right to feel that initial skepticism, that gentle resistance to an idea that seems to give human qualities to something so vast and seemingly empty as the vacuum between stars. Space, after all, is not a body with nerves, not a brain with neurons firing, not a creature with sensors warning it of damage or danger. Space is, as far as our instruments can tell, mostly nothing. An almost perfect vacuum punctuated by the occasional atom, the passing photon, the invisible fields that carry forces across impossible distances. How could such a thing feel anything at all, let alone something as specific and biological as pain? And yet, the more gently we hold this question, the more it begins to open like a flower that only blooms in darkness. Because what if we're not talking about pain as we usually understand it, not the sharp signal of injury or the dull ache of inflammation, but something else entirely, something that might require us to expand our definition of feeling itself? What if the universe, in ways we're only beginning to glimpse through our most sensitive instruments and our most adventurous theories, has properties that mirror, in some vast and distributed way, the kinds of responses and sensitivities we associate with living things? What if the fabric of spacetime, which we know can bend and stretch and ripple, might in some poetic or even literal sense experience strain, experience stress, experience the cosmic equivalent of what we, in our small biological bodies, interpret as sensation? You see, we live in a time when our understanding of the universe is undergoing profound shifts, when the old picture of space as a static stage on which matter performs its dance is giving way to something far more dynamic, far more interconnected, far more alive with possibility. We've discovered that space itself can be warped by mass and energy, that it can carry waves that stretch and compress the very fabric of reality as they pass, that it expands and perhaps even tears in ways we're only beginning to understand. We've found that the universe is not just expanding but accelerating in its expansion, pushed by something we call dark energy but don't truly comprehend, and we've realized that most of the matter in the universe is invisible to us, dark matter whose presence we know only through its gravitational effects, like sensing an invisible hand by the way it moves the curtains. In this context, the question of whether space could feel becomes less absurd and more intriguing, not because we're going to prove tonight that the universe has consciousness in any conventional sense, not because we're going to claim that stars scream or that galaxies suffer, but because the question itself opens doorways to thinking about our cosmos in new ways, to recognizing patterns and connections that might otherwise remain hidden, to approaching the vast mystery of existence with a combination of scientific rigor and poetic imagination that neither alone could achieve. Tonight, we're going to walk that edge between the known and the unknown, between the measured and the imagined, between the equations that describe reality and the metaphors that help us feel our place within it. Think about your own body for a moment, the one that's resting right now as you listen to these words. That body is made of atoms forged in the hearts of stars, atoms that have existed for billions of years, atoms that have been part of rocks and rivers, plants and animals, clouds and crystals before they came together to create the temporary pattern that is you. Your body is mostly empty space, the gaps between your atomic nuclei and their electrons proportionally as vast as the gaps between stars, and yet somehow, through the extraordinary emergence of biological organization, this collection of ancient stardust has become capable of feeling. You can sense pressure and temperature, pleasure and pain, the weight of gravity and the lightness of floating in water. Your nervous system, built from the same fundamental particles that make up distant galaxies, has developed the ability to detect changes in its environment, to respond to stimuli, to create the subjective experience of sensation from the objective facts of physics and chemistry. Now, this doesn't mean that the universe has a nervous system like yours, doesn't mean that galaxies have neurons or that dark matter feels lonely. But it does mean that the ability to respond to stimuli, to be affected by changes, to exist in states of greater or less attention or equilibrium is not unique to biological systems, but might be a more fundamental property of reality itself, expressed in different ways at different scales and levels of organization. When a massive object warps space-time around it, creating what we call a gravitational field, is this not a kind of response, a kind of sensitivity? When gravitational waves ripple outward from colliding black holes, carrying information about that cosmic catastrophe across billions of light years, is this not a kind of communication, a kind of feeling transmitted through the very fabric of existence? Let me be clear about what we're doing here tonight. We're not trying to prove anything in the scientific sense, not making claims that would stand up to peer review or experimental verification. Instead, we're engaging in a kind of philosophical meditation, a thought experiment that uses the language of science and the freedom of imagination to explore what it means to exist in a universe that might be far stranger and more wonderful than our everyday experience suggests. We're taking seriously the idea that consciousness, awareness, or something like feeling, might not be confined to biological brains, but might be a more fundamental feature of reality, expressed in ways we're only beginning to recognize. This is not New Age mysticism or wishful thinking, but a legitimate philosophical position called Panpsychism that has been debated by serious thinkers for centuries and is experiencing something of a renaissance in contemporary philosophy of mind. The beauty of this question, what if space itself could feel pain, is that it forces us to think about familiar concepts in unfamiliar ways. Pain, after all, is not just suffering. Pain is information, a signal that something needs attention, that boundaries have been crossed, that change is necessary. Pain is how biological systems protect themselves, how they learn to avoid damage, how they maintain their integrity in a world full of challenges. If we abstract away from the specifically biological aspects of pain and think about it as a kind of information processing, as a response to stress or strain that promotes adaptation or avoidance, then suddenly the question of whether space could feel pain becomes a question about whether the universe processes information about its own state, whether it responds to stresses and strains in ways that preserve or restore some kind of cosmic equilibrium. And we know that it does, at least in certain ways. When matter and energy concentrate too densely in one region of space, the result is a black hole, a kind of cosmic quarantine that prevents that extreme density from affecting the rest of the universe in ways that might destabilize it. When the early universe was filled with tiny quantum fluctuations, those variations in density became the seeds of all the large-scale structure we see today, as if the cosmos was responding to its own initial conditions by organizing itself into the patterns of galaxies and voids that we observe. When dark energy accelerates the expansion of space, pulling galaxies apart from each other, might this be understood as a kind of cosmic response to some tension or disequilibrium we don't yet understand? You're lying there, or sitting there, in your own small corner of this vast universe, and your body is performing countless adjustments and responses that you're not even aware of. Your blood pressure is being regulated, your temperature maintained, your immune system is patrolling for threats, your cells are repairing damage and replacing themselves. Most of this happens below the threshold of consciousness, an endless dance of response and adaptation that keeps you alive without your having to think about it. What if the universe operates on similar principles, but at scales so vast and timescales so long that we've only recently developed the ability to detect them? What if what we call the laws of physics are actually more like habits or tendencies, patterns of response that the universe has developed over cosmic time? Consider how we've discovered that the universe has a kind of memory encoded in the cosmic microwave background radiation, that faint afterglow of the Big Bang that still fills all of space with a nearly uniform temperature just a few degrees above absolute zero. This radiation carries within it tiny variations, fluctuations that tell the story of the universe when it was only 380,000 years old, and these fluctuations became the seeds of all the structure we see today. In a sense, the universe remembers its own infancy, and that memory shapes everything that comes after. Is this so different from how your own body carries memories? Not just in your brain, but in your immune system, in your scars, in the patterns of tension in your muscles. The more we learn about the universe, the more it seems to behave less like a machine and more like something organic, something that grows and evolves and responds to its own internal dynamics. Galaxies are born, live and die, though on timescales that dwarf human comprehension. Stars go through life cycles, burning hydrogen into helium, creating heavier elements in their cores, eventually dying in ways that depend on their mass, sometimes explosively seeding space with the materials for new generations of stars and planets. The universe itself seems to have gone through phase transitions, moments when its fundamental properties change dramatically, like water freezing into ice or boiling into steam. These are not the behaviors of a static, insensate void, but of something dynamic, something that changes and develops over time, something that might, in ways we don't yet have language for, experience those changes. Tonight, as we explore this question together, we're going to journey from the smallest scales we can measure to the largest structures we can observe. We're going to consider what modern physics tells us about the nature of space and time, about the quantum foam that might exist at the tiniest scales, where space itself becomes uncertain and probabilistic. We're going to explore how gravity works not as a force but as the curvature of space-time, how massive objects create distortions that we experience as attraction, how the universe might be filled with invisible dimensions curled up too small to detect. We're going to think about consciousness and information, about how patterns of organization might give rise to awareness, about whether the universe itself might be processing information in ways that create something like experience. But we're going to do all of this gently, slowly, with the kind of patience that the universe itself seems to embody. There's no rush here, no urgent revelation waiting at the end, no dramatic conclusion that will change everything. Instead, we're going to let these ideas wash over us like waves on a shore, each one bringing something new to examine before it recedes, leaving us slightly changed, slightly more aware of the mystery we're embedded in. We're going to use science not as a tool for certainty, but as a gateway to wonder, and we're going to use imagination not as an escape from reality, but as a way of sensing possibilities that our current knowledge only hints at. The question of whether space itself could feel pain is really a question about the nature of existence itself, about what it means to be part of a universe that produced beings capable of asking such questions. You and I, temporary arrangements of matter and energy, have somehow developed the ability to contemplate the cosmos that created us, to feel wonder and curiosity about our origins and our context. Is this not itself a kind of miracle, a kind of evidence that the universe is more than just dead matter following mechanical laws? The fact that you can lie there, listening to these words, feeling perhaps a little sleepy, a little curious, a little skeptical, a little open to possibility means that the universe has developed the ability to examine itself, to question itself, to imagine itself as other than it appears. Some physicists and philosophers have suggested that consciousness might be fundamental to reality, not emerging from complex arrangements of matter, but present from the beginning in some basic form, becoming more complex and integrated as matter organizes itself into more complex patterns. This view, sometimes called cosmopsychism, suggests that the universe itself might have some form of awareness, not like human consciousness, but something more basic, more distributed, perhaps what we might call proto-consciousness or pure experience. If this were true, then asking whether space could feel pain would be like asking whether the ocean can have waves, not a category error, but a question about how a fundamental property manifests at different scales. But even if consciousness is not fundamental, even if it only emerges from certain complex arrangements of matter like brains, the question remains fascinating. Because we know that the universe tends toward increasing complexity, from simple hydrogen atoms to complex molecules to self-replicating systems to conscious beings. This tendency, sometimes called the arrow of complexity, suggests that the universe might have an inherent drive toward creating patterns that can process information, respond to their environment, and perhaps eventually experience something like sensation or awareness. In this view, we are not separate from the universe, but expressions of its tendency toward complexity and consciousness, local concentrations of awareness in a cosmos that might be gradually waking up to itself. As you lie there, breathing slowly, feeling the weight of your body against whatever surface supports you, you are participating in this cosmic process. Your consciousness, however it arises, is the universe becoming aware of itself in this particular location, at this particular moment. Your thoughts about whether space could feel pain are the cosmos contemplating its own nature, using the biological computer of your brain to process possibilities that might or might not correspond to reality. And in a very real sense, through you and through billions of other conscious beings throughout the universe, space is feeling, is experiencing, is knowing itself from the inside. The journey we're beginning tonight is not about finding definitive answers to these vast questions. It's about dwelling in the questions themselves, letting them expand our sense of what's possible, what's mysterious, what's wonderful about existence. We're going to move slowly, thoughtfully, like explorers in a landscape that reveals itself gradually, where each vista opens onto new territories of thought and imagination. We're going to use the tools of science, the insights of philosophy, and the freedom of speculation to create a kind of meditation on the nature of reality, one that might help you see the universe and your place in it in new ways. So settle in, let your breathing slow, let the tensions of the day begin to dissolve. We have hours ahead of us, hours to explore ideas that stretch from the quantum to the cosmic, from the beginning of time to its possible ends, from the nature of consciousness to the structure of space itself. There's no need to grasp everything, no test at the end, no requirement except to be present with these ideas and let them work on you in whatever way they will. Some of what we discuss might seem too strange to believe. Some might resonate deeply with intuitions you've always had. Some might simply wash over you as you drift towards sleep, becoming part of your dreams. The universe you're embedded in is approximately 13.8 billion years old, and it has spent all that time evolving, complexifying, creating conditions where matter can organize itself into patterns capable of contemplating their own existence. You are one of those patterns, a temporary but meaningful arrangement of particles and forces that has somehow developed the ability to wonder about the whole. Tonight, we're going to honor that wonder, follow it wherever it leads, and see what insights or simply what interesting thoughts emerge from considering whether the vast reaches of space might, in some sense we're only beginning to imagine, have the capacity to feel. Remember, as we go forward, that every atom in your body, every particle of your being, is in constant contact with the fabric of space-time. You're not in the universe like a marble in a box. You are of the universe, woven into its fabric, inseparable from the cosmic web that connects all things. The gravitational field of every star in the sky passes through your body, though too faintly to detect. The electromagnetic radiation from distant galaxies, light that has travelled for billions of years, is arriving at your location right now, some of it absorbed by your atoms, becoming part of your warmth. You're already intimate with the cosmos in ways that our ordinary awareness doesn't register, already participating in the vast network of relationships and responses that might, if we expand our definitions enough, constitute something like cosmic feeling. What if pain, or something like it, is how the universe experiences extremes, boundaries, transitions? What if the event horizons of black holes, those boundaries beyond which nothing can escape, create something like sensation in the fabric of space-time? What if the collision of galaxies, played out over millions of years, generates something like feeling in the vast, slow dance of gravity and dark matter? What if the quantum foam at the smallest scales, where particles pop into and out of existence in timeframes too brief to measure, creates a kind of background sensation, a cosmic static that might be the universe's equivalent of the continuous low-level sensory input you experience but don't consciously notice? These are the kinds of questions we'll be exploring, not with the expectation of proof or certainty, but with the open curiosity that makes us human, that makes us capable of science and poetry, logic and dreams. We'll draw on real observations from telescopes and particle accelerators, real theories from physics and cosmology, but we'll also allow ourselves the freedom to speculate, to imagine, to wonder what might be true beyond the current borders of our knowledge. Because those borders are always expanding, and what seems impossible to one generation often becomes the established science of the next. The physicist Niels Bohr once said that the opposite of a correct statement is a false statement, but the opposite of a profound truth may well be another profound truth. Tonight, we're not seeking correct statements so much as profound questions. Questions that might not have single answers, but that open up new ways of thinking about reality. The question of whether space could feel pain is one of these. A question that might be wrong in its literal interpretation, but right in its invitation to think more deeply about the nature of existence, consciousness, and our place in the cosmic story. As we prepare to dive deeper into these ideas, take a moment to appreciate where you are right now. You're on a planet spinning at over 1,000 miles per hour at the equator, orbiting a star at 67,000 miles per hour, which itself is orbiting the center of the Milky Way at 514,000 miles per hour, which is moving through space relative to other galaxies at even greater speeds, and yet to you, everything feels still, quiet, stable. This is the magic of relative motion, the way the universe allows each observer to experience their own frame of reference as if it were at rest. Even in your stillness, you're hurtling through space at unimaginable speeds, participating in cosmic dances nested within dances, movements within movements, all choreographed by the gentle curvature of spacetime that we call gravity. You begin in your room, in this familiar space that you know so well, where the walls create a boundary between inside and outside, between the personal and the vast, between the known territory of your daily life and the infinite mystery that stretches above your ceiling, beyond your roof, past the atmosphere and into the depths of space that we're contemplating together. This room, whether it's small or large, cluttered or spare, is your immediate universe, the space you can touch and see and navigate without thought. The air around you, invisible but present, moves gently with your breath, carries the sounds of my voice to your ears, maintains the pressure that keeps your body functioning. You might not think of it often, but you're at the bottom of an ocean of air, an atmosphere that thins gradually as altitude increases until it becomes indistinguishable from the vacuum of space. No clear boundary, just a gradual transition from something to almost nothing. Let's begin our journey outward from this intimate space, moving slowly, thoughtfully, like a camera pulling back in an impossibly long, smooth motion that will carry us from the personal to the universal. If you could rise straight up from where you are now, passing through your ceiling as if it weren't there, you'd first see your home from above, its roof just one among many if you're in a city, or perhaps standing alone if you're in a rural area. The patterns of human habitation become visible from this height, the ways we cluster together for warmth and community, the roads and paths that connect one place to another like neurons connecting across a brain, carrying the traffic of human life and commerce and connection. Rising higher, perhaps a few hundred feet now, you'd see your neighborhood, your district, the larger patterns of your town or city. The lights, if it's nighttime where you are, create constellations on the ground that mirror in their own way the constellations above. Points of brightness in the darkness, each one representing a life, a family, a story unfolding. During the day, you'd see the colours and textures of human civilization mixed with whatever nature remains or has been cultivated. Parks and gardens, rivers and coastlines, the interface between the built environment and the natural world that preceded it and will outlast it. At 1,000 feet, individual people become difficult to distinguish, and at 10,000 feet, even buildings begin to merge into patterns, textures, the urban fabric that we've woven across the landscape. This is the view from small aircraft, where you can still make out familiar landmarks but where the scale begins to shift from human to geographical. Mountains reveal their true shapes, rivers show their meandering paths, forests become seas of green or brown depending on the season, and deserts stretch out in their austere beauty. You're still well within the atmosphere here, in the realm of clouds and weather, where water vapour condenses and precipitates, where winds carry seeds and dust and sometimes the smoke from distant fires. As we continue to rise in our imagination, passing the heights where commercial aircraft cruise at 30 or 40,000 feet, the curve of Earth begins to become visible, subtle at first, then more pronounced. The atmosphere, which seemed infinite from ground level, reveals itself as a thin shell, a delicate blue haze that contains all the air that has ever been breathed, all the weather that has ever been weathered, all the life that depends on this narrow zone of gases held to the planet by gravity. It's sobering to realise how thin this life-supporting layer really is, proportionally thinner than the skin on an apple, and yet it's enough to maintain the temperatures and pressures and chemical compositions that allow beings like us to exist and contemplate our existence. At the edge of space, conventionally defined as 100 kilometres or about 62 miles above Earth's surface, though the atmosphere continues in ever thinner traces far beyond this, you would see the planet in its full glory and fragility. The blue of the oceans, which cover more than 70% of the surface, dominates the view, broken by the browns and greens and whites of continents, the swirling patterns of clouds that reveal the constant motion of the atmosphere, the terminator line between day and night creeping across the surface as the planet rotates. From here, no human conflicts are visible, no borders except those created by geography, no evidence of the struggles and triumphs that seem so important from ground level. Earth appears as what it is, a single system, a living world, the only known harbour for consciousness in an otherwise apparently unconscious cosmos. But we're just beginning our journey outward. As we continue to rise, to move away from Earth, the planet shrinks from a vast sphere filling our view to a ball, then a marble, then a point of light. The moon comes into view as a separate world, no longer the flat disk we see from Earth, but a sphere in its own right, cratered and ancient, locked in its eternal dance with Earth, showing always the same face to its larger partner. The Earth-Moon system, which seemed like everything when we were on the surface, becomes just another example of the gravitational relationships that structure the universe at every scale. Moving outward still, we pass the orbit of the International Space Station, that extraordinary achievement of human cooperation and engineering, where a handful of people live and work in microgravity, conducting experiments and maintaining humanity's most distant permanent outpost. We pass the orbits of the thousands of satellites that circle Earth, providing communication, navigation, weather monitoring and scientific observation, an artificial constellation that we've created to extend our senses and connect our civilizations. Each of these objects follows the laws of orbital mechanics, balancing velocity against gravity, tracing ellipses and circles that would continue indefinitely if not for the tiny drag of the ultra-thin atmosphere that still exists even at these heights. As Earth recedes behind us, becoming just another point of light, albeit a blue one, we begin to appreciate the true scale of the solar system. The Sun, which seemed to orbit Earth from our ground-based perspective, reveals itself as the true centre of our local cosmic neighbourhood, a star of medium size and middle age, converting 600 million tons of hydrogen to helium every second, radiating energy that warms worlds and drives weather, enables photosynthesis, and powers the entire ecosystem of at least one planet. The Sun's gravity holds the solar system together, its radiation pressure pushes against dust and gas, its magnetic field extends far beyond the orbits of the planets, creating a bubble in interstellar space that we call the heliosphere. We pass Mercury, scorched and cratered, racing around the Sun in just 88 Earth days. A world of extremes where the sunward side can reach 800 degrees Fahrenheit, while the night side plunges to minus 290. We pass Venus, shrouded in clouds of sulfuric acid, its surface hot enough to melt lead due to a runaway greenhouse effect that turned what might have been an Earth-like world into a vision of hell. Each world we pass has its own character, its own history, its own response to the fundamental forces that shape planetary evolution. These are not just balls of rock and gas, but complex systems that process energy and information in their own ways, that have weather and geology, that change over time in response to internal and external influences. Mars appears red and rusty, a world that once had rivers and lakes and possibly oceans that might once have harboured life and might harbour it still in some subsurface refuge. The asteroid belt spreads out between Mars and Jupiter, not the dense field of rocks portrayed in fiction, but a vast region where millions of objects orbit, separated by distances that typically measure in the hundreds of thousands of miles. These asteroids are remnants from the solar system's formation, pieces that never coalesced into a planet, and they carry information about the conditions that existed when the Sun was young and the planets were just beginning to form. Jupiter looms ahead, the giant of our solar system, more massive than all the other planets combined, a world of storms and clouds and radiation, surrounded by its own system of moons that range from tiny captured asteroids to worlds like Ganymede, larger than Mercury, and Europa, which hides an ocean beneath its icy surface that might contain more water than all of Earth's oceans combined. Jupiter's Great Red Spot, a storm larger than Earth that has raged for centuries at least, demonstrates the kind of long-term stability that can emerge from chaos, a pattern that persists despite the constant turbulence that creates and maintains it. Saturn presents its magnificent rings, structures of ice and rock that from a distance look solid, but are actually composed of countless individual particles, each following its own orbit, together creating patterns of waves and gaps that respond to the gravitational influences of Saturn's many moons. The rings are ephemeral on cosmic timescales, probably only a few 100 million years old and destined to eventually dissipate, a reminder that even the most beautiful and seemingly permanent features of our cosmic neighbourhood are temporary, part of the constant change that characterises the universe. We continue outward past Uranus, tipped on its side for reasons we don't fully understand, and Neptune, where winds blow at speeds approaching that of sound, past the Kuiper Belt where Pluto and countless other icy worlds orbit in the deep cold far from the sun's warmth. And finally, we approach the heliopause, the boundary where the solar wind meets the interstellar medium, where our sun's influence gives way to the greater galactic environment. The Voyager spacecraft have crossed this boundary, humanity's first ambassadors to interstellar space, carrying golden records with sounds and images from Earth, messages in bottles thrown into the cosmic ocean. But even as we leave the solar system behind, we've barely begun to explore the true scale of space. The nearest star, Proxima Centauri, is over 4 light-years away, meaning that light, the fastest thing in the universe, takes over 4 years to make the journey. If the solar system was shrunk down so that Earth was the size of a pea, Proxima Centauri would still be nearly 200 miles away. The spaces between stars are so vast that even though our galaxy contains hundreds of billions of stars, you could travel in most directions for light years without encountering anything larger than a grain of dust. This is the ocean of space we're contemplating, an ocean not of water but of vacuum. Yet not empty vacuum, but something filled with fields and forces, with radiation and particles, with dark matter we can't see and dark energy we don't understand. Space itself, this apparent nothingness between things, is the medium through which all influences propagate, the fabric that connects all things, the stage on which the cosmic drama unfolds. And just as Earth's oceans are not uniform but have currents and temperatures, chemistry and life, the ocean of space has its own structure, its own dynamics, its own kinds of weather and seasons played out on scales we can barely comprehend. Our Milky Way galaxy, home to our Sun and several 100 billion other stars, is a spiral structure about 100,000 light-years across, a vast wheel of stars and gas and dust rotating slowly, completing one rotation every 250 million years or so. We're located about 26,000 light-years from the galactic centre, in a relatively quiet suburb between major spiral arms, in what's sometimes called the local bubble, a region of relatively low-density gas created by ancient supernova. The galaxy has structure at every scale: individual stars, binary and multiple star systems, star clusters both open and globular, stellar nurseries where new stars are born, stellar graveyards where old stars have died, and threading through it all, the mysterious dark matter that outweighs visible matter by about 6 to 1. When we look at other galaxies, and we can see billions of them with our telescopes, we see that they too are not randomly distributed but form patterns at larger scales. Galaxies cluster together in groups and clusters, and these clusters connect along filaments of the cosmic web, vast structures that stretch across billions of light years, with enormous voids between them where very few galaxies exist. This cosmic web, the largest structure we know of, emerged from tiny quantum fluctuations in the early universe, amplified by gravity over cosmic time into the architecture of reality we observe today. The idea that this vast structure might in some sense feel, might respond, might experience, seems at first absurd, and yet consider the similarities between the cosmic web and other networks we know to be associated with information processing and perhaps consciousness. The human brain contains about 86 billion neurons connected by trillions of synapses, creating a network that somehow generates or embodies consciousness. The cosmic web contains hundreds of billions of galaxies connected by gravity and dark matter, creating a network whose full properties we're only beginning to understand. The timescales are vastly different. The mechanisms of connection are different, but the mathematical structure, the topology of connection, shows surprising similarities. Researchers have found that the network of neurons in the human brain and the network of galaxies in the cosmic web share similar statistical properties, similar distributions of connections, similar patterns of clustering and hierarchy. This doesn't prove that the universe is conscious, but it suggests that the kinds of structures we associate with information processing and complexity exist at the largest scales as well as at biological scales. The universe seems to naturally create networks, from the quantum to the cosmic, and networks are substrates for communication, for information flow, for the kinds of processes that, at least in one case we know of, give rise to consciousness and feeling. Think about how a network processes information. A signal enters at one point and propagates through connections, being modified and modulated by the structure of the network, eventually producing responses at other points. In the brain, these signals are electrical and chemical, propagating through neurons and synapses. In the cosmic web, the signals might be gravitational waves, or the flows of dark matter, or the pressure waves in the intergalactic medium. The timescales are vastly different. What takes milliseconds in the brain might take millions of years in the cosmic web, but time is relative, as Einstein taught us, and what matters might not be the absolute rate of information processing, but the complexity and integration of the processing itself. We know that galaxies respond to each other gravitationally, that they can collide and merge, that they can trigger star formation in each other through tidal interactions, that they can strip gas from each other as they pass. These are responses, reactions, a kind of cosmic behavior that emerges from the fundamental laws of physics, but creates patterns and structures that those laws alone don't fully predict. When two galaxies approach each other, their interaction is not a simple collision, but a complex dance that can last billions of years, with stars and gas clouds responding to the changing gravitational field, with new stars being born from the compressed gas, with the galaxies eventually settling into a new configuration that carries the memory of their interaction. Is this so different from how neurons in your brain respond to each other? How the firing of one influences the firing of others? How patterns of activation create thoughts and feelings and memories? The mechanisms are different, the scales are different, but the principle of responsive interaction, of information being processed through a network of connections, seems to operate at both scales. And if consciousness or feeling can emerge from one kind of network, why not from another, albeit one operating on scales and timescales that dwarf our ordinary experience? The ocean of space is not uniform but has weather of its own. Solar winds blow from stars, carrying charged particles that interact with planetary magnetospheres to create auroras. Cosmic rays, particles accelerated to nearly the speed of light by supernovae and other violent events, streak through space in all directions, occasionally colliding with atoms in our atmosphere to create showers of secondary particles. Gravitational waves ripple outward from accelerating masses, stretching and squeezing space itself as they pass. Magnetic fields thread through galaxies and even through the intergalactic medium, channeling charged particles and influencing the formation of structures. All of this activity, all of this dynamics, suggests that space is not a passive container, but an active participant in cosmic evolution. The vacuum itself seethes with quantum fluctuations, virtual particles appearing and disappearing on timescales too brief to measure directly, but having measurable effects on atoms and forces. What we call empty space is actually a plenum, full of fields and potentialities, constantly fluctuating, never truly at rest. Even in the deepest voids between galaxies, where the density of matter is lower than the best vacuum we can create on Earth, space itself is alive with activity at the quantum level. The question of whether this activity constitutes something like feeling depends on how we define feeling. If feeling requires biological neurons and synapses, then obviously space doesn't feel. But if feeling is more fundamentally about response, about the processing of information, about systems changing their state based on inputs, then space might feel in ways we're only beginning to imagine. The curvature of space-time around a massive object could be thought of as a kind of sensation, the fabric of reality responding to the presence of matter and energy. The propagation of gravitational waves could be thought of as a kind of communication, information about cosmic events spreading through the fabric of space at the speed of light. Consider how your own feelings arise. At the most basic level, they're patterns of electrochemical activity in your nervous system, neurons firing in response to stimuli, neurotransmitters crossing synapses, complex cascades of cause and effect that somehow give rise to the subjective experience of emotion. But zoom out a bit, and feelings are also about your whole body responding, your heart rate changing, your breathing deepening or quickening, hormones releasing into your bloodstream, muscles tensing or relaxing. Feeling is a whole system phenomenon, not localized to any one part, but emerging from the integrated activity of many parts working together. Now imagine space as a system, not a biological system, but a physical system of enormous complexity. It has structure at every scale, from the quantum foam at the Planck length to the cosmic web spanning billions of light years. It processes information in the form of fields and waves and particles. It responds to changes with massive objects warping spacetime, with energy density affecting expansion rates, with quantum fluctuations seeding the formation of structures. Could this vast system, in some sense we don't yet understand, have something analogous to feelings, not emotions like fear or joy, but more fundamental responses to its own state and changes in that state? This is not a question we can answer definitively with our current understanding, but it's a question worth contemplating, worth holding gently in our minds as we try to understand our place in the cosmos. Because if space itself could feel, even in the most abstract and non-biological sense, then we are not conscious beings in an unconscious universe, but rather localized intensifications of awareness in a cosmos that might have some form of awareness throughout. We would be like whirlpools in a stream, temporary patterns of organization that allow the stream to experience itself in a particularly intense and self-reflective way. The ocean metaphor is particularly apt because oceans on Earth are not uniform, but have structure and dynamics at every scale. There are the great currents like the Gulf Stream, carrying warm water thousands of miles and influencing climate on a global scale. There are smaller eddies and gyres, tides and waves, thermoclines and haloclines where waters of different temperatures or salinities meet. Marine life is not distributed uniformly, but concentrates where conditions are right, where nutrients well up from the depths, where temperatures are suitable, where currents bring food. The ocean processes information about wind and temperature, about the rotation of the Earth and the pull of the Moon, integrating all these influences into its complex behavior. Space, too, has its currents and structures. Galaxies flow along the filaments of the cosmic web, drawn by gravity toward the massive clusters that act as nodes in the network. Dark matter flows in streams, remnants of smaller galaxies that have been torn apart by tidal forces. Gas flows from the intergalactic medium into galaxies, where it can cool and condense to form new stars. Energy flows from stars into space, radiation that carries information about stellar compositions and processes across cosmic distances. All of these flows interact, influence each other, create the complex tapestry of cosmic evolution that we observe. In the depths of Earth's oceans, we've discovered ecosystems that exist in total darkness, around volcanic vents that spew superheated, mineral-rich water into the cold abyss. Life in these places has adapted to conditions that would seem impossible, using chemosynthesis instead of photosynthesis, thriving in the absence of sunlight. These discoveries have expanded our understanding of where and how life might exist, suggesting that the boundaries of the possible are wider than we once imagined. Similarly, our growing understanding of space reveals environments and phenomena that challenge our preconceptions, from the intense gravity near black holes to the mysterious properties of dark energy. from the quantum uncertainty at the smallest scales to the accelerating expansion of the universe itself. As you lie there, perhaps feeling drowsy now, your consciousness flickering like a candle flame in the vast darkness, you are participating in this cosmic ocean in ways both obvious and subtle. The gravity of every object in the universe reaches you, however faintly. The cosmic microwave background radiation, the afterglow of the Big Bang, passes through your body, has been passing through it since before you were born, will continue passing through the space you occupy long after you're gone. Neutrinos from the sun, from distant supernovae, from the Big Bang itself, stream through you by the trillions every second, almost never interacting but occasionally, very rarely, colliding with one of your atoms and depositing a tiny amount of energy. You're not separate from the ocean of space but immersed in it, part of it, a temporary arrangement of its substance that has somehow developed the ability to contemplate the whole. Your thoughts about whether space could feel are themselves a kind of feeling that space is having through you, localized and intense, but not separate from the larger processes that created and sustain you. Every element in your body heavier than hydrogen was forged in the nuclear furnaces of stars or in the violent explosions of supernovae. You are literally made of cosmic processes, stellar evolution condensed into biological form, the universe looking back at itself through eyes that stars created. The boundary between you and space is not as clear as it might seem. Your body is mostly empty space, the gaps between your atomic nuclei and their electrons proportionally vast. The forces that hold you together, electromagnetic and nuclear, extend beyond your apparent boundaries, interacting with the fields that fill all of space. You're more like a wave pattern in the ocean of space than a separate object within it, a standing wave of matter and energy that maintains its form while constantly exchanging substance with its environment. With every breath, you take in atoms that have been part of countless other beings, and with every exhalation, you release atoms that will become part of others. You're a process, not a thing, a verb rather than a noun, a temporary but meaningful eddy in the cosmic flow. You imagine space not as empty, not as nothing, but as something with texture and structure, something that can be influenced and shaped, something that responds to what moves through it and rests within it. This is not just poetic metaphor but actual physics, the understanding that emerged from Einstein's general theory of relativity and has been confirmed by countless observations and experiments in the centuries since. Space and time are not separate entities but aspects of a unified spacetime, a four-dimensional fabric that can curve and stretch, compress and twist, carry waves and store energy. This fabric is the stage on which all cosmic dramas play out, but unlike a rigid stage, it participates in the performance, bending and flexing in response to the actors upon it. To understand this, let's start with something familiar, a stretched rubber sheet or a piece of spandex fabric. If you place a heavy ball in the center, it creates a depression, a curvature in the fabric. Now, if you roll a marble near this depression, it will curve toward the heavy ball, not because the ball is pulling on it with some mysterious force, but because it's following the straightest possible path through the curved space. This is a two-dimensional analogy for what happens in four-dimensional space-time. Mass and energy cause space-time to curve, and objects moving through space-time follow the straightest paths they can, which in curved space-time become curved trajectories that we interpret as gravitational attraction. But this analogy, helpful as it is, only hints at the true strangeness and beauty of space-time. The fabric of space is not made of anything in the conventional sense. It is the foundation upon which the concept of things depends. It has properties, it can be measured, it has a geometry, it can carry energy. But it's not composed of atoms or particles in the way matter is. It's more fundamental than matter, the backdrop against which matter and energy exist and interact. And this backdrop is not passive but dynamically responsive, constantly adjusting its shape in response to the distribution of mass and energy within it. Think about what this means on a cosmic scale. Every star creates a dimple in space-time, a gravitational well that extends outward, weakening with distance but never quite reaching zero. Planets orbit within these dimples, following paths determined by the curvature of space. Galaxies create deeper wells, and clusters of galaxies create vast basins in the fabric of space-time that draw in matter from millions of light-years away. The entire observable universe has a shape, a geometry that depends on its total mass-energy content, and that determines its ultimate fate, whether it will expand forever, collapse back on itself, or balance precisely between the two. This fabric can also carry waves, ripples in spacetime itself that propagate outward from accelerating masses. When two massive objects orbit each other, binary stars, binary black holes, binary neutron stars, they create a constantly changing gravitational field that sends out waves like a cosmic lighthouse beam sweeping through space. These gravitational waves stretch and squeeze space as they pass, making distances slightly longer and shorter in an alternating pattern that moves at the speed of light. The effect is incredibly tiny. Even waves from colliding black holes only change distances by less than the width of a proton. Yet we've built instruments sensitive enough to detect these minute distortions. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, consists of two facilities, one in Louisiana and one in Washington state, each with two 4-kilometer-long arms arranged in an L shape. Laser beams bounce back and forth between mirrors at the ends of these arms, and when a gravitational wave passes through, it slightly changes the length of the arms, causing the laser beams to go in and out of phase with each other. The first detection, made in September 2015, captured the final fraction of a second of two black holes spiraling together and merging, an event that happened 1.3 billion years ago. The signal, when converted to audio frequencies, sounds like a brief chirp, the billion-year-old echo of a cosmic catastrophe. Think about what this means. Space itself can be plucked like a guitar string, can ring like a bell, can carry information about events that happened when Earth was populated only by single-celled organisms. The fabric of space-time is not inert but resonant, able to transmit and preserve patterns, to be affected by, and to affect the matter and energy within it. When those black holes merged, they converted 3 solar masses worth of matter into pure gravitational wave energy in less than a second, making them briefly the most powerful source in the universe, outshining all the stars in all the galaxies combined, but shining in gravitational waves rather than light. Since that first detection, we've observed dozens of gravitational wave events. More black hole mergers, neutron star collisions, possibly even black holes swallowing neutron stars. Each event has its own signature, its own pattern of stretching and squeezing that tells us about the masses involved, their spins, their distances, their orientations. We're learning to read the vibrations of space-time itself, to hear the universe in a completely new way. And what we're hearing suggests that space is constantly humming, with gravitational waves, from countless sources, a cosmic symphony of space-time vibrations that we're only just beginning to perceive. The fabric of space-time also responds to energy density in a way that determines the expansion of the universe itself. In 1998, astronomers studying distant supernovae made a shocking discovery. The expansion of the universe is not slowing down as expected, but accelerating. Something is pushing space apart, causing it to expand faster and faster. We call this something dark energy, and it appears to be a property of space itself, an intrinsic tension or pressure that becomes more dominant as the universe expands and matter becomes more dilute. Dark energy now accounts for about 68% of the total energy density of the universe, and its nature remains one of the deepest mysteries in physics. If space has an intrinsic energy, a kind of tension that drives it to expand, could this be thought of as a kind of sensation, a cosmic restlessness, a fundamental discomfort with stasis? This is pure speculation, of course, but it's striking that empty space is not nothing but something with properties, with energy, with a kind of agency that affects the evolution of the universe on the largest scales. The vacuum of space is not empty, but full of virtual particles that pop into existence and annihilate in timeframes too brief to observe directly, full of fields that extend throughout the universe, full of what physicists call zero-point energy, the minimum energy that a quantum system can have. At the quantum scale, space becomes even stranger. The uncertainty principle tells us that we cannot know both the position and momentum of a particle with perfect precision, and this uncertainty extends to the fabric of space itself. At scales smaller than the Planck length, about 10 to 35 meters, space might not be smooth but foamy, constantly fluctuating, with tiny wormholes and black holes appearing and disappearing in a quantum froth that underlies the apparent smoothness we observe at larger scales. This quantum foam, if it exists, would mean that space at its most fundamental level is not stable but seething with activity, constantly creating and destroying microscopic structures in a restless dance of possibility. John Wheeler, the physicist who coined the term black hole, also proposed that space at the quantum scale might be like a foam with a complex ever-changing topology. He imagined that if you could zoom in far enough, you would see space constantly creating tiny tunnels and bridges, handles and holes, a dynamic geometry that averages out to the smooth spacetime we observe at larger scales, but that reveals wild complexity at the smaller scales. This vision of quantum foam suggests that space itself might be processing information at the most fundamental level, constantly computing its own geometry, its own structure, its own properties. The idea that space might be computational, that reality might emerge from information processing at the quantum scale, has gained traction among some physicists. The holographic principle, for instance, suggests that all the information in a volume of space can be encoded on its boundary, like a hologram that creates a three-dimensional image from information stored on a two-dimensional surface. Black holes provide evidence for this. Their entropy, a measure of information content, is proportional not to their volume, but to their surface area. This suggests that information, not matter or energy, might be the most fundamental aspect of reality, and that space itself might be emergent from more basic informational processes. If space is informational at its base, if it processes and stores information, then the question of whether it could feel becomes a question about the relationship between information processing and consciousness. We know that our brains process information, and that this processing somehow gives rise to, or correlates with, conscious experience. We don't understand how this happens, the so-called hard problem of consciousness, but we know that it does. Could space, processing information at scales from the quantum to the cosmic, have some form of experience, some kind of feeling that emerges from its computational activity? Consider how the fabric of spacetime stores information about what has passed through it. Gravitational lensing allows us to see galaxies that would otherwise be hidden behind other galaxies, their light bent around the intervening mass by the curvature of spacetime. The cosmic microwave background carries information about the state of the universe 380,000 years after the Big Bang. Tiny temperature variations that record the seeds of all future structure. Gravitational waves carry information about their sources across billions of light years, allowing us to observe events that happened before Earth existed. Space remembers, in a sense, preserving and transmitting information across vast distances and times. The fabric of spacetime also exhibits something like elasticity. When a gravitational wave passes, space stretches and compresses, but then returns to its original shape. When a massive object moves through space, it creates a wake in the gravitational field, but space itself is not permanently deformed. This resilience, this ability to respond to stress and then recover, is reminiscent of elastic materials, of systems that can be strained but have a tendency to return to equilibrium. Could this elasticity be thought of as a kind of sensation, space feeling the strain of distortion and the relief of relaxation? Near extreme objects like black holes, the fabric of spacetime is stretched to its limits. At the event horizon of a black hole, space is curved so severely that not even light can escape. Time dilation becomes extreme, with time passing more slowly in strong gravitational fields relative to weak ones. An observer falling into a black hole would experience normal time, but to an outside observer, they would appear to slow down and freeze at the event horizon, their last image redshifted into invisibility. The fabric of space-time is twisted so intensely near a rotating black hole that it drags space around with it, a phenomenon called frame dragging that has been measured around Earth, though the effect is tiny. These extreme distortions might be thought of as cosmic stress points, places where the fabric of space-time is under maximum strain. If space could feel, would these be areas of intense sensation, cosmic pressure points where the normal rules break down and new phenomena emerge? The singularities predicted at the centers of black holes, where density becomes infinite and space-time curvature becomes undefined, might represent something like cosmic trauma, points where the fabric of reality itself is torn or broken, though most physicists believe that quantum effects not yet fully understood prevent true singularities from forming. The fabric of space-time also responds to phase transitions, moments when the fundamental properties of space change dramatically. In the very early universe, as it cooled from the unimaginable temperatures of the Big Bang, space went through several phase transitions, similar to how water turns to ice but involving changes in the fundamental forces and particles. During cosmic inflation, a hypothetical period in the first fraction of a second after the Big Bang, space expanded exponentially, growing by a factor of at least 10^26 in less than 10-hour war, 32 seconds. This dramatic expansion stretched quantum fluctuations to cosmic scales, seeding the structure we see today. These phase transitions might be thought of as cosmic state changes, moments when space itself transforms from one configuration to another. If space could feel, these transitions might be experienced as profound shifts, like the universe awakening to new possibilities, new ways of being. The fact that our universe went through precisely the right series of phase transitions to allow for the existence of atoms, stars, planets, and life might suggest either incredible fine-tuning or the existence of many universes with different histories, different phase transitions, different properties of space itself. The vacuum of space also exhibits what physicists call vacuum pressure, or vacuum energy, the energy of empty space itself. This is not zero, as classical physics would suggest, but has a small positive value that drives the accelerating expansion of the universe. The vacuum is not inert but active, constantly creating virtual particle pairs that exist for brief moments before annihilating. These quantum fluctuations give the vacuum a kind of texture, a graininess at the smallest scales that might be thought of as the universe's way of exploring possibilities, constantly testing different configurations of matter and energy before settling back into the vacuum state. Recent theories suggest that space might have extra dimensions beyond the 3 spatial dimensions and 1-time dimension we experience. These extra dimensions might be curled up too small to detect, or we might be confined to a 3-dimensional brain embedded in a higher dimensional space. If these extra dimensions exist, they would add layers of complexity to the fabric of space-time, additional degrees of freedom that might allow for phenomena we haven't yet imagined. The way space responds to matter and energy might depend on the geometry of these hidden dimensions, adding richness to the universe's ability to process and respond to information. String theory, one attempt to unify quantum mechanics and general relativity, proposes that the fundamental constituents of reality are not point particles, but tiny vibrating strings, and that the properties of particles depend on how these strings vibrate. In this view, space itself might emerge from the collective behavior of these strings, making space-time not fundamental, but emergent, like temperature emerging from the motion of molecules. If space emerges from more fundamental processes, then asking whether space can feel might be like asking whether temperature can feel. The question might need to be reframed in terms of the underlying processes that give rise to space. The fabric of space-time also exhibits non-locality, the ability for quantum-entangled particles to instantaneously correlate their properties regardless of the distance between them. This suggests that space, at least at the quantum level, is not simply a container that separates things, but a medium that maintains connections, that allows for instant correlation across any distance. Einstein called this spooky action at distance and was troubled by it, but experiments have confirmed that quantum entanglement is real, and that space allows for connections that transcend our ordinary understanding of separation and locality. This non-locality might be thought of as space's way of maintaining coherence, of keeping track of relationships and correlations across vast distances. If space can maintain instantaneous quantum correlations, might it also maintain other kinds of connections we haven't yet discovered? Might the fabric of space-time be more like a vast neural network, with quantum entanglement serving as the synapses that allow for information integration across cosmic distances? This is highly speculative, but the fact that space exhibits non-local properties suggests that our ordinary understanding of it, as mere distance between objects, is incomplete. As you lie there, perhaps feeling the weight of your body against whatever surface supports you, you're experiencing the curvature of space-time directly. The force you feel as gravity is actually your body's tendency to follow the straightest path through space-time being prevented by the surface beneath you. If that surface were removed, you would fall, following a geodesic through curved space-time until you encountered another object. The sensation of weight is the sensation of accelerating through space-time, of being prevented from following your natural path by the electromagnetic forces in the atoms of the floor or bed that support you. Your body is also creating its own tiny distortion in spacetime, an infinitesimal curvature that extends outward from your mass. Every atom in your body contributes to this distortion, and the combined effect, while too small to measure with current technology, is real. You're not just in spacetime, but actively shaping it, contributing to its geometry, participating in the cosmic dance of matter and space. The boundary between you and spacetime is not sharp, but fuzzy, your gravitational field extending infinitely outward, weakening with distance but never quite reaching zero, connecting you gravitationally to every other mass in the universe. The fabric of space-time near Earth is also affected by our planet's rotation, creating a tiny frame-dragging effect that causes orbiting satellites to precess slightly. This effect, predicted by general relativity and confirmed by the Gravity Probe B mission, shows that rotating masses don't just curve space-time but twist it, creating a kind of gravitational vortex that affects the motion of nearby objects. Earth's rotation literally drags space around with it, though the effect is so small that it took decades of technological development to create instruments sensitive enough to measure it. As we've explored the fabric of space-time, we've seen that it's not passive but active, not empty but full, not rigid but flexible, not local but connected. It responds to matter and energy by curving, carries waves that transmit information across cosmic distances, exhibits quantum fluctuations at the smallest scales, and drives the expansion of the universe at the largest scales. It stores information, maintains correlations, undergoes phase transitions, and might emerge from even more fundamental processes we don't yet understand. If we expand our definition of feeling to include any system that responds to stimuli, processes information, and changes its state based on inputs, then spacetime certainly feels in this abstract sense. It feels the presence of mass and energy through curvature, feels the acceleration of masses through gravitational waves, feels quantum fluctuations through vacuum energy, feels the cosmic evolution through expansion. These are not feelings in the biological sense, not emotions or sensations as we experience them, but they are responses, reactions, a kind of cosmic sensitivity that pervades all of existence. The question is not whether spacetime responds, we know it does, but whether these responses constitute something more than mechanical reactions, whether there's something it's like to be spacetime, whether the universe has an interior experience corresponding to the exterior behaviors we observe. This is ultimately a philosophical question that science alone cannot answer, but by understanding how spacetime works, how it processes information, how it responds to influences, we can at least appreciate the complexity and richness of the fabric that underlies all existence. As you drift deeper into relaxation, perhaps beginning to feel sleepy, you might imagine yourself not as separate from spacetime but as a pattern within it, a temporary concentration of energy and information that arose from the fabric and will eventually dissolve back into it. Your thoughts, your feelings, your consciousness itself might be ways that spacetime experiences itself, local intensifications of the information processing that occurs throughout the cosmos. You are not in the universe, you are the universe, experiencing itself subjectively, feeling itself from the inside, even if only in this small region, for this brief time. The fabric of spacetime continues its patient work all around you and within you, carrying gravitational waves from distant cosmic events, maintaining quantum correlations across vast distances, expanding slowly but inexorably, processing information in ways we're only beginning to understand. It's a fabric that bends and listens, that responds and remembers, that connects all things in an intricate web of relationships and influences. Whether it feels in any sense we would recognize is unknowable, but that it participates actively in the cosmic story, that it's not mere background but a central character in the drama of existence, is undeniable. And as you rest there, supported by this fabric, shaped by it, shaping it in return with your small but real gravitational influence, you might sense yourself as part of something vastly larger, older, and more mysterious than everyday experience suggests. You're a ripple in the fabric of spacetime, a wave that arose from the cosmic ocean and will eventually return to it. But for now, for this precious moment, you are here, aware, wondering about the nature of the fabric that makes your existence possible, the fabric that bends and listens, that stretches and remembers, that connects all things in ways both obvious and subtle, both local and non-local, both scientific and perhaps, just perhaps, something approaching the mystical. You think of pain not as punishment, not as cruelty, not as something to be feared or avoided at all costs, but as the body's quiet language, the way your cells communicate urgency, the way your nervous system says, something has changed here, something needs attention, something requires a response. Pain, in this understanding, is not an enemy, but a teacher, not a curse, but a form of deep biological wisdom that has kept countless organisms alive through billions of years of evolution. It's the sharp withdrawal from a hot surface that prevents burns, the ache that tells you to rest an injured limb so it can heal, the discomfort that guides you away from danger and towards safety. Pain is information, densely packed, immediately compelling, impossible to ignore, and in this sense it might be one of the most fundamental forms of communication that exists in living systems. Now, as you lie there in the darkness, perhaps with your eyes closed, perhaps gazing at the ceiling or the stars if you can, see them through your window, I want you to consider what it might mean if the universe itself had something analogous to this kind of communication system. Not pain as suffering, not pain as agony, but pain as signal, as message, as the cosmos noting its own stresses and strains and responding accordingly. What if the extreme curvatures near black holes, the stretching of space during cosmic inflation, the tearing that might occur in the far future as dark energy accelerates expansion, what if these are like the universe's version of sensation, its way of registering extremes, boundaries, transitions? Think about how pain works in your own body at the cellular level. When cells are damaged, they release chemical signals, prostaglandins and other molecules that trigger inflammation, that sensitize nerve endings, that create the cascade of responses we experience as pain. This is not random or purposeless, but highly organized, a sophisticated system for damage detection and response coordination. The pain signal travels from the site of injury through peripheral nerves to the spinal cord, where it can trigger immediate reflexive responses, and then to the brain, where it becomes conscious experience and can guide deliberate action. The entire system is about communication, about different parts of the body sharing information about their state and coordinating responses to maintain or restore health. In the cosmos, we see analogous patterns of communication and response, though operating through entirely different mechanisms and on vastly different scales. When a massive star exhausts its nuclear fuel and begins to collapse, the process sends out signals in multiple forms. First, there's a flood of neutrinos, ghostly particles that barely interact with matter, but carry away most of the energy of the collapse. These neutrinos stream out through the star and into space at nearly the speed of light, carrying information about the stellar catastrophe to anyone with instruments sensitive enough to detect them. Hours or days later, the shockwave from the collapse reaches the star's surface, and it explodes as a supernova, sending out light that can outshine an entire galaxy and creating heavy elements that will eventually become part of new stars, planets, and possibly living beings. This stellar death is traumatic on a cosmic scale, temperatures reaching billions of degrees, matter compressed to nuclear densities, spacetime curved so severely that it can trap light itself if the star is massive enough to form a black hole. If the universe could feel pain, might not such events register as cosmic trauma, intense localized experiences that send ripples of consequence outward through space and time? The gravitational waves from such collapses propagate outward, stretching and squeezing space itself, carrying information about the event to distant regions of the universe. The explosion enriches the surrounding space with heavy elements, changing the chemical composition of future star-forming regions. The remnant, whether a neutron star or black hole, continues to affect its surroundings for billions of years, a kind of cosmic scar that never fully heals. But let's pull back from these dramatic events and consider more subtle forms of cosmic sensation. Throughout the universe, matter is constantly responding to forces, adjusting its configuration, seeking equilibrium or being driven away from it. In the vast clouds of gas and dust that fill the spaces between stars, atoms and molecules are constantly colliding, exchanging energy, cooling through radiation, heating through shock waves from nearby stars or supernovae. These clouds are not uniform but have complex structures, filaments and knots, voids and condensations, all constantly evolving in response to the interplay of gravity, pressure, magnetic fields, and radiation. When a region of such a cloud becomes dense enough, gravity overcomes pressure and collapse begins, eventually forming new stars. This process is not sudden but gradual, taking millions of years, and it's exquisitely sensitive to conditions. A nearby supernova can trigger star formation by compressing gas clouds, or it can prevent it by heating and dispersing them. The spiral arms of galaxies are density waves that trigger star formation as gas clouds pass through them, creating the beautiful spiral patterns we observe. These might be thought of as zones of cosmic sensitivity, regions where the universe is actively creating new structures, new possibilities, new ways of organizing matter and energy. The language of pain in biological systems is not just about damage, but also about healing, growth, and adaptation. When you exercise vigorously, you create tiny tears in your muscle fibers, and the mild pain you feel afterward is part of the process by which your body rebuilds those fibers stronger than before. When bones are stressed by impact or load, they respond by increasing their density in those areas, a process guided by the mechanical signals that might register as discomfort. Pain can be productive, creative, transformative, not just a signal of harm but a catalyst for improvement. Similarly, in the cosmos, what might appear as trauma or stress can be creative. The collision of galaxies, which might seem catastrophic, rarely results in stars actually colliding because the spaces between them are so vast. Instead, the gravitational interactions trigger new waves of star formation, creating stellar nurseries where the next generation of stars and planets will be born. The tidal forces that tear apart small galaxies as they fall into larger ones also create streams of stars that trace beautiful arcs through space and can seed the larger galaxy with fresh gas for star formation. What might be experienced as cosmic pain, if such a thing exists, could also be cosmic creativity, transformation, evolution. Consider the concept of tidal forces, the differential, gravitational pull that occurs when one side of an object is closer to a massive body than the other side. These forces stretch objects, and if strong enough, can tear them apart in what's called spaghettification near black holes. For a human falling into a stellar mass black hole, tidal forces would become lethal long before reaching the event horizon, stretching the body lengthwise while compressing it horizontally. This might seem like pure cosmic horror, but tidal forces are also responsible for some of the most dynamic and beautiful phenomena in the universe. The tides in Earth's oceans, caused by the differential pull of the moon and sun, have been crucial for life's evolution, creating intertidal zones where organisms had to adapt to changing conditions, possibly facilitating the transition from sea to land. The tidal heating of Jupiter's moon Europa maintains a liquid ocean beneath its icy surface, a potential habitat for life. The tidal locking of the moon to Earth, so that it always shows us the same face, creates a stable configuration that has helped regulate Earth's climate over billions of years. Tidal forces are the universe's way of objects feeling each other's presence across space, responding to gradients in the gravitational field that carry information about mass distributions and movements. Now let's think about dark matter, that mysterious substance that makes up about 85% of all matter in the universe, but doesn't interact with light, doesn't form atoms, doesn't participate in the chemistry that makes life possible. We know it exists only through its gravitational effects, the way it bends light through gravitational lensing, the way it holds galaxies and clusters together with its invisible mass, the way it shaped the formation of cosmic structure in the early universe. Dark matter is like a cosmic nervous system we can barely detect, a vast network of invisible mass that guides the evolution of visible matter through gravitational influence alone. If the universe has sensations, might dark matter be part of how it feels itself? The dark matter halos that surround galaxies extend far beyond the visible stars, creating vast spheres of gravitational influence that determine how galaxies move and interact. Streams of dark matter from disrupted dwarf galaxies flow through larger galaxies like invisible rivers, affecting the orbits of stars in ways we're only beginning to map. The cosmic web itself is primarily made of dark matter, with ordinary matter following its gravitational template like iron filings following magnetic field lines. This invisible architecture might be thought of as the universe's proprioceptive system, its way of sensing its own structure and coordinating the movement of its visible components. Then there's dark energy, even more mysterious than dark matter, the force or property that's causing the expansion of the universe to accelerate. Dark energy acts like a kind of cosmic tension, a pressure, that pushes space apart, growing stronger as the universe expands and matter becomes more dilute. If dark matter is like the universe's nervous system, dark energy might be like a chronic condition, a constant background sensation that influences everything else. The acceleration it causes means that distant galaxies are not just moving away from us, but accelerating away, and eventually, in the far future, they will pass beyond our cosmic horizon, becoming forever unreachable. This accelerating expansion might be thought of as a kind of cosmic restlessness, an inability to settle into a stable configuration. The universe seems to be pulling itself apart, slowly but inexorably, driven by this mysterious dark energy that makes up about 68% of its total energy density. Is this cosmic discomfort, a universe that cannot find equilibrium, that's driven to expand by some fundamental tension we don't yet understand? Or is it cosmic growth, the universe creating more space, more room for possibility, more canvas for the cosmic artwork to unfold upon? The interaction between dark matter, dark energy, and ordinary matter creates a complex dynamic that evolves over cosmic time. In the early universe, matter density was high enough that gravity dominated, slowing the expansion. But as the universe expanded and matter diluted, dark energy became dominant, beginning to accelerate the expansion about 5 billion years ago. This transition from deceleration to acceleration might be thought of as a cosmic state change, a shift in the universe's dominant sensation from the attractive pull of gravity to the repulsive push of dark energy. Let's consider another form of cosmic communication, electromagnetic radiation in all its forms, from radio waves to gamma rays. Every atom in the universe that's above absolute zero is constantly emitting and absorbing photons, participating in an endless exchange of electromagnetic information. Stars broadcast their presence across the cosmos, their light carrying information about their temperature, composition, age, and motion. Gas clouds absorb and re-emit radiation, creating spectral signatures that tell us about their chemical makeup and physical conditions. Even the cosmic microwave background, that faint afterglow of the Big Bang, is a form of electromagnetic communication from the early universe to the present. This constant exchange of photons might be thought of as the universe's way of feeling itself through light. Every surface that absorbs light is warmed by it, experiencing the energy of distant stars as heat. Every atom that absorbs a photon of the right energy jumps to a higher energy state, a kind of atomic excitement that might be the most basic form of sensation. The pressure of light, though tiny, can push on objects, accelerate particles, shape the tails of comets. Light is not just illumination, but a form of touch that operates across cosmic distances, allowing objects to feel each other's presence across the vast emptiness of space. Magnetic fields provide another layer of cosmic sensation. These invisible fields thread through galaxies, guide charged particles, shape the solar wind, protect planets from cosmic rays. The Earth's magnetic field, generated by convection in its liquid iron core, creates a protective bubble that has been essential for life's evolution, deflecting harmful radiation that would otherwise strip away our atmosphere. The Sun's magnetic field, twisted and amplified by the Sun's rotation and convection, creates sunspots, solar flares, and coronal mass ejections that send waves of charged particles through the solar system, creating auroras when they interact with planetary magnetic fields. On larger scales, magnetic fields in galaxies affect star formation, channel cosmic rays, and may play a role in the acceleration of particles to extreme energies. The magnetic fields in galaxy clusters can be millions of light years across, invisible scaffolding that influences the motion of charged particles and the formation of structures. These fields carry information about electric currents and particle motions, creating another layer of cosmic communication, another way the universe might sense and respond to changes within itself. Cosmic rays, particles accelerated to nearly the speed of light by supernovae, black holes, and other extreme events, provide yet another form of cosmic communication. These particles stream through space in all directions, occasionally colliding with atoms in Earth's atmosphere to create showers of secondary particles. Some cosmic rays have energies far beyond what our most powerful particle accelerators can achieve, carrying information about the most extreme processes in the universe. When a cosmic ray particle that has travelled for millions of years across intergalactic space finally collides with an atom in our atmosphere, it's like a message from the distant universe, a tiny packet of information about cosmic violence delivered after an incredibly long journey. The universe also communicates through neutrinos, those ghostly particles that barely interact with matter but stream through space in vast numbers. Every second, trillions of neutrinos from the sun pass through your body without interacting, carrying information about the nuclear reactions in the sun's core. Neutrinos from supernovae, from the Big Bang, from cosmic ray interactions, fill the universe with a barely detectable background of information. Detecting these neutrinos requires enormous detectors, often buried deep underground to shield them from other particles. But when we do detect them, they tell us about processes hidden from electromagnetic observation, like the fusion reactions in the sun's core or the collapse of a star's core in a supernova. If we think of pain as a signal that promotes adaptation and survival in biological systems, we might see analogous processes in cosmic evolution. Galaxies that venture too close to massive clusters can be stripped of their gas by ram pressure, losing their ability to form new stars. This might seem destructive, but it also prevents the galaxy from using up its gas too quickly, potentially extending the lifetime of its existing stars. Planets that orbit too close to their stars have their atmospheres stripped away by stellar wind. But this same process might deliver water and organic molecules to planets in more habitable zones. The concept of feedback is crucial in both biological pain systems and cosmic processes. In your body, pain creates negative feedback loops that promote healing and prevent further damage. You pull your hand away from a hot stove, you rest an injured ankle, you avoid foods that cause digestive distress. In the cosmos, we see similar feedback mechanisms. When star formation in a galaxy becomes too vigorous, the energy from young stars and supernovae heats and disperses the gas, shutting down further star formation until the gas can cool and condense again. When a black hole at the center of a galaxy accretes too much matter, it produces jets and radiation that heat the surrounding gas, preventing further accretion until conditions change. These feedback mechanisms might be thought of as the universe's way of self-regulating, of maintaining balance, of preventing extremes that could be destructive to its overall structure and evolution. Just as pain prevents you from damaging yourself beyond repair, cosmic feedback mechanisms prevent galaxies from forming all their stars at once, prevent black holes from consuming everything around them, prevent the universe from evolving too quickly or too slowly. The universe seems to have built-in regulatory mechanisms that guide its evolution, that maintain a kind of cosmic homeostasis even as it expands and evolves. As you contemplate these ideas lying there in the quiet darkness, you might begin to sense that the distinction between living and non-living, between feeling and non-feeling, between conscious and unconscious, might not be as sharp as we usually assume. The universe exhibits properties we associate with living systems: growth, evolution, self-regulation, communication, response to stimuli, adaptation. It processes information on scales from the quantum to the cosmic, integrates this information through various fields and forces, and responds in ways that suggest something more than mere mechanical reaction. The question is not whether the universe behaves in ways analogous to living, feeling systems. It clearly does, but whether these behaviors are accompanied by any form of experience, any subjective dimension, any felt quality. This is the hard problem of consciousness writ large. How does objective processing become subjective experience? We don't know how this happens in the human brain, so we certainly can't say whether or how it might happen at cosmic scales. But the fact that we, as parts of the universe, have subjective experience suggests that the capacity for experience is inherent in the cosmos, at least in certain configurations. Perhaps consciousness and feeling are not binary properties that a system either has or doesn't have, but exist on a spectrum with different degrees and kinds of experience possible at different scales and levels of organization. A bacterium responding to chemical gradients might have a minimal form of experience, a plant turning toward light another form, an insect avoiding danger yet another. By this logic, the universe itself, with its vast networks of interaction and information processing, might have forms of experience utterly unlike ours, but still deserving of the term. If pain is fundamentally about information that demands response, about signals that cannot be ignored, about states that require change, then the universe is full of pain-like phenomena. Every gravitational wave that stretches space is a signal that cannot be ignored by any mass in its path. Every supernova that enriches surrounding space with heavy elements creates changes that affect all future star and planet formation in that region. Every collision between galaxies sets in motion responses that play out over billions of years. These might not be pain in any sense we would recognize, but they are cosmic imperatives, signals that demand response, information that shapes future evolution. The universe seems to be telling itself about itself constantly, through light and gravity, through particles and waves, through fields and forces. Every part affects every other part, even if the influence is tiny and delayed by the finite speed of light. This vast network of communication and influence might constitute something like a cosmic nervous system, not centralized like ours, but distributed throughout space and time, processing information not in milliseconds but in millions of years, responding not with muscle contractions but with the formation of structures, the evolution of galaxies, the birth and death of stars. As you rest there, perhaps feeling your own body's subtle signals, the rhythm of your breath, the beat of your heart, the tiny tensions and relaxations of muscles, you might recognize yourself as a localized intensification of the universe's capacity to feel. Your pain and pleasure, your thoughts and emotions, are not separate from cosmic processes but are cosmic processes, taking place in a small region of space for a brief interval of time. The calcium ions that flow through your neurons when you think were forged in the cores of massive stars. The electrical gradients that drive neural signals are the same electromagnetic force that carries starlight across the cosmos. The quantum processes that might underlie consciousness operate according to the same principles that govern the behavior of particles throughout the universe. In this view, asking whether space itself could feel pain is perhaps asking the wrong question. Space does feel pain, through us, through every sentient being that has ever existed or will exist. We are not observers of the universe but participants in it, not separate from space but patterns within it, not conscious beings in an unconscious cosmos, but localized intensifications of whatever cosmic properties allow for consciousness. Our pain is the universe's pain, experienced locally but connected to the whole through the endless web of relationships and influences that bind all things together. But beyond our biological pain, there might be other forms of cosmic sensation we can barely imagine. The stress on space-time near massive objects, the quantum fluctuations of the vacuum, the tension of dark energy, the flows of dark matter, all of these might constitute forms of cosmic experience that have no analogue in biological systems. We are like cells in a vast body, aware of our own cellular processes but only dimly conscious of the larger organism of which we are part. Our pain might be just one note in a cosmic symphony of sensation that plays out on scales we can observe but not directly experience. You picture the universe as a quiet room, a vast chamber that still glows with the last traces of its own beginning, a faint warmth that fills every corner of space, every cubic centimetre of the cosmos from here to the edge of the observable universe and beyond. This glow, this cosmic microwave background radiation that we've abbreviated to CMB, is not something you can see with your eyes, for it shines in wavelengths far longer than visible light, in the microwave portion of the spectrum where your eyes are blind but where our radio telescopes can perceive with extraordinary precision. It's the oldest light in the universe, released when the cosmos was only 380,000 years old, when it first became transparent to radiation, when atoms first formed from the soup of electrons and nuclei that filled all of space. To understand this ancient light and what it tells us about whether space might feel, might respond, might have something like sensation, we need to journey back to those early moments, to a universe vastly different from the one we inhabit today. Imagine space itself at a temperature of about 3000 degrees Kelvin, hot enough to glow orange-red if our eyes could have existed to see it, filled with a plasma of electrons and protons that scattered light endlessly, making the entire universe opaque, like being inside a star. For 380,000 years after the Big Bang, light could not travel freely through space but bounced from electron to electron in an endless cosmic pinball game, unable to stream freely across the cosmos. Then, As the universe expanded and cooled, a profound transition occurred. The temperature dropped below the point where electrons and protons could combine into hydrogen atoms, and suddenly, within a relatively brief period of perhaps a few thousand years, the universe became transparent. The light that had been trapped in the cosmic plasma was suddenly free to travel, to stream across space unimpeded, carrying with it information about the universe at that moment of liberation. This light has been travelling ever since, for over 13.8 billion years, cooling as the universe expanded, its wavelength stretching from visible light to infrared to microwave, until today it has a temperature of just 2.7 to 25 degrees above absolute zero. This cosmic microwave background is remarkably uniform, the same temperature in every direction to within 1 part in 100,000. This uniformity tells us something profound. The early universe was in thermal equilibrium, every part in communication with every other part, sharing energy and information until a common temperature was reached. But it's the tiny variations, the slight warm spots and cool spots that differ by just millionths of a degree, that carry the most interesting information. These variations are the seeds from which all structure in the universe grew, the slight overdensities and underdensities that gravity would amplify over billions of years into the cosmic web of galaxies and voids we see today. The first detection of the CMB came by accident in 1964, when Arno Penzias and Robert Wilson, working with a radio antenna in New Jersey, found a persistent noise they couldn't eliminate. They tried everything to remove this noise, even clearing out pigeon droppings from their antenna, but the signal persisted, coming equally from all directions. What they had discovered was the afterglow of the Big Bang itself, the cooled remnant of the universe's hot, dense beginning. This discovery, which earned them the Nobel Prize, was the first direct evidence that the universe had a beginning, that it had evolved from a hot, dense state to the cool, sparse cosmos we inhabit today. But the real revelations came with more precise measurements. The COBE satellite, launched in 1989, made the first detection of the tiny temperature variations in the CMB, showing that the early universe was not perfectly smooth, but had slight ripples, quantum fluctuations stretched to cosmic scales by inflation. These ripples, though incredibly small, were the gravitational seeds that would grow into galaxies and clusters. COBE's measurements were like finding the universe's baby picture, seeing the patterns that would determine its future development. The UMAP satellite, which operated from 2001 to 2010, provided even more detailed maps of these temperature fluctuations, revealing patterns that told us about the universe's age, composition, and geometry. UMAP showed us that the universe is 13.77 billion years old, that ordinary matter makes up only 4.6% of its total energy density, that dark matter accounts for 24% and dark energy for 71%. It confirmed that space is geometrically flat on large scales, neither curved like a sphere nor saddle-shaped, but extending infinitely in all directions like an endless sheet of paper. The Planck satellite, operated by the European Space Agency from 2009 to 2013, pushed our vision of the CMB to even greater precision, mapping temperature variations down to millionths of a degree and detecting the polarization of the CMB light. This polarization carries information about how the light last scattered off electrons in the early universe, providing another layer of information about cosmic conditions when the universe was young. Planck's measurements have given us our most precise values for the fundamental parameters of cosmology, the numbers that describe the universe's composition, age, and expansion rate. But what do these measurements tell us about whether space might feel, might sense, might respond to what happens within it? Consider first what these temperature variations represent. They are not just random noise but have a specific pattern, a power spectrum that peaks at particular angular scales. The largest variations correspond to regions that were just coming into causal contact at the time the CMB was released, regions that had just had time to communicate with each other through the speed of light since the Big Bang. Smaller variations represent acoustic oscillations, sound waves in the primordial plasma, regions that had compressed and rarefied as gravity pulled matter together and radiation pressure pushed it apart. These acoustic oscillations are particularly fascinating. The early universe was filled with sound, not sound that any ear could hear, but pressure waves travelling through the plasma at about half the speed of light. These waves were driven by the competition between gravity, trying to compress regions of slightly higher density, and radiation pressure trying to expand them. The pattern of peaks in the CMB power spectrum tells us about these cosmic sound waves frozen in place when the universe became transparent. It's as if the universe preserved a record of its own voice, its own acoustic signature from a time when it was young and hot and dense. The polarization of the CMB adds another layer to this cosmic sensation. Light becomes polarized when it scatters off electrons in a particular way, and the pattern of polarization in the CMB tells us about the motion of matter when the light was released. There are two types of polarization patterns, called E modes and B modes, with E modes being created by density fluctuations and velocity gradients, while B modes can be created by gravitational waves from the early universe. The detection of B mode polarization would be evidence of gravitational waves from cosmic inflation, ripples in spacetime from the universe's first fraction of a second, though such detection remains controversial and unconfirmed. Think about what this means. The universe has preserved in its background radiation not just a temperature map, but a record of motion, of acoustic oscillations, possibly of gravitational waves, all encoded in the subtle properties of light that has been travelling for nearly 14 billion years. This is not a dead static record, but a dynamic one, still evolving as the CMB photons encounter matter and are slightly deflected by gravitational lensing, picking up new information about the distribution of mass along their path to our detectors. The CMB also shows us something remarkable about the universe's geometry and connectivity. The fact that regions of the CMB that appear widely separated in the sky have nearly the same temperature tells us that these regions were once in causal contact, able to exchange information and come to thermal equilibrium. But in the standard Big Bang model without inflation, these regions would never have had time to communicate given the finite speed of light. This is the horizon problem, and its solution, cosmic inflation, suggests that the universe underwent a period of exponential expansion that took regions that were once in contact and stretched them far apart, preserving their common temperature while separating them by distances that light has not had time to travel since. This inflationary period, if it occurred, would have been a time of extreme cosmic sensation, with space itself expanding faster than light, which is possible because it's space itself expanding, not objects moving through space. Quantum fluctuations, normally confined to subatomic scales, would have been stretched to cosmic sizes, becoming the seeds of all future structure. The universe would have been in a kind of excited state, a false vacuum with enormous energy density that drove the exponential expansion until it decayed into the hot Big Bang we're more familiar with. This transition from inflation to the Big Bang would have been a cosmic phase transition, perhaps something like the universe exhaling after holding its breath, releasing enormous amounts of energy that became the matter and radiation filling space. Recent observations have revealed additional subtle features in the CMB that hint at even more complex cosmic sensations. There are suggestions of anomalies, patterns that don't quite fit our standard models. The axis of evil, a somewhat tongue-in-cheek name for an unexpected alignment of the larger-scale CMB fluctuations, suggests that the universe might have a preferred direction, though this remains controversial. The cold spot, a region of the CMB that's unusually cold and large, might be evidence of a cosmic texture, a defect in space-time, or perhaps the imprint of a collision with another universe in a vast multiverse, though more mundane explanations are also possible. The CMB also interacts with the matter it encounters on its long journey to our detectors, picking up additional information about the universe's structure and evolution. The Sunyaev-Zeldovich effect occurs when CMB photons pass through hot gas in galaxy clusters, getting boosted to higher energies by collisions with fast-moving electrons. This effect allows us to detect galaxy clusters independent of their distance, providing another probe of cosmic structure. The integrated Sachs-Wolfe effect occurs when CMB photons gain or lose energy by falling into and climbing out of gravitational wells that are evolving due to dark energy, providing evidence for cosmic acceleration. Gravitational lensing of the CMB by all the matter between us and the surface of last scattering creates subtle distortions in the temperature and polarization patterns, distortions that carry information about the distribution of both dark and ordinary matter throughout cosmic history. By analyzing these distortions, we can create maps of the dark matter distribution, seeing the invisible scaffolding that guides the formation of visible structures. It's as if the universe uses the CMB as a backlight to reveal its otherwise invisible components, a cosmic X-ray showing the skeleton of dark matter that supports the flesh of ordinary matter. The study of the CMB has also revealed something profound about the nature of space itself. It appears to be geometrically flat on the largest scales we can observe. This flatness is puzzling because it requires the universe's total energy density to be precisely at the critical value that separates eternal expansion from eventual recollapse. A universe with even slightly more or less energy density would be noticeably curved on large scales, yet we see no such curvature. This fine-tuning problem is another piece of evidence for cosmic inflation, which would have driven the universe toward flatness regardless of its initial curvature, like inflating a balloon until its surface appears flat on small scales. But there's more to the cosmic background than just the microwave radiation. There's also a cosmic neutrino background, relic neutrinos from when the universe was only 1 second old, when it was hot enough for neutrinos to be in thermal equilibrium with other particles. These neutrinos decoupled from other matter when the universe cooled below about 10 billion degrees, and they've been streaming freely through space ever since. We haven't detected these relic neutrinos directly. They're too low in energy for our current detectors, but we know they must exist, and they affect the CMB and structure formation in subtle ways that we can measure indirectly. There might also be a gravitational wave background, a confusion of gravitational waves from countless sources throughout cosmic history. These would include waves from cosmic inflation, from phase transitions in the early universe, from the formation of the first black holes, from all the mergers and collisions and accelerations that have occurred since the beginning. This gravitational wave background would be incredibly difficult to detect, but it would carry information about cosmic events that produce no electromagnetic radiation, events hidden from our telescopes, but not from the fabric of spacetime itself. The universe might even have a cosmic consciousness background, if consciousness is indeed a fundamental property that becomes organized and amplified in certain configurations of matter. This is pure speculation, far beyond what science can currently address, but if experience is a basic feature of reality, then perhaps there's a background of minimal experience filling all of space, occasionally organizing into the more complex and integrated forms of consciousness we recognize in living beings. The CMB would then be just one layer of cosmic memory, with other layers encoding different aspects of the universe's experience of itself. As we study these cosmic backgrounds, we're essentially doing cosmic archaeology, digging through layers of light and particles and waves to understand the universe's history. Each background was laid down at a different time, under different conditions, carrying information about different aspects of cosmic evolution. The CMB from 380,000 years after the Big Bang, the neutrino background from 1 second after, the gravitational wave background potentially from the first fraction of a second. Together, they form a kind of cosmic sedimentary record, each layer telling part of the story of how the universe evolved from its hot, dense beginning to the vast, cool cosmos we see today. The patterns in these backgrounds also tell us about the universe's capacity for self-organization. The acoustic peaks in the CMB power spectrum show that the early universe could support coherent oscillations on vast scales, coordinated behavior emerging from the interplay of fundamental forces. The fact that these oscillations seeded the formation of galaxies and clusters shows that the universe has a kind of memory, with patterns established in the first few 100,000 years determining structures that wouldn't fully form for billions of years. This is not unlike how experiences in early childhood can shape personality and behavior throughout life, though the mechanisms and timescales are vastly different. The CMB also reveals the universe's sensitivity to initial conditions, those tiny quantum fluctuations in the early universe, variations of perhaps 1 part in 100,000, were enough to seed all the structure we see today. A slightly denser region would gravitationally attract more matter, becoming denser still, eventually collapsing to form galaxies and clusters. A slightly less dense region would lose matter to its surroundings, becoming a cosmic void. This extreme sensitivity to initial conditions is a hallmark of complex systems, systems capable of rich behavior, and perhaps, in some sense, we don't yet understand experience. As you lie there in the darkness, you're immersed in these cosmic backgrounds. CMB photons are passing through your body right now, about 400 per cubic centimeter, carrying their ancient information about the universe's youth. Relic neutrinos, about 300 per cubic centimeter, stream through you undetected. Gravitational waves from distant cosmic events ripple through the space you occupy, stretching and squeezing you by amounts too small to perceive. You're not separate from these cosmic backgrounds, but embedded in them, part of the ongoing story they tell. Your own body is warm, about 310 Kelvin, enormously hot compared to the 2.7 Kelvin of the CMB. You're a warm spot in a cold universe, a local concentration of energy and organization that stands out dramatically from the background. But you're not violating any cosmic principles. You're using energy flows to maintain your organization, taking in food and oxygen, radiating heat into your surroundings, participating in the universe's general trend toward increasing entropy while maintaining local order. You're like a small eddy in the cosmic flow, a temporary pattern that the universe is exploring, a way for the cosmos to experience being human for a brief time. The discovery and study of the CMB has transformed our understanding of the universe from a collection of objects in space to a unified, evolving system with a definite history and potentially predictable future. We can now trace cosmic evolution from the first fraction of a second to today, seeing how quantum fluctuations became galaxies, how simple hydrogen and helium became the rich chemistry of life, how a nearly uniform plasma became the complex cosmic web we observe. This is not just intellectual knowledge, but a kind of cosmic self-awareness, the universe developing the capacity to observe and understand its own history. The precision of CMB measurements has also revealed tensions in our cosmological models. The expansion rate measured from the CMB doesn't quite match the rate measured from nearby supernovae. The amount of clustering observed in the current universe is slightly less than the CMB would predict. These tensions might be due to measurement errors, or they might be hints that our models are incomplete, that there are aspects of cosmic evolution we don't yet understand. Perhaps dark energy is not constant but evolving. Perhaps there are additional neutrino species or other particles we haven't detected. Perhaps the universe's geometry is more complex than we've assumed. These uncertainties are not failures but opportunities, chances to deepen our understanding of cosmic processes. They suggest that the universe still holds surprises, that our current picture, successful as it is not complete. The cosmos continues to reveal new aspects of itself as our instruments become more sensitive and our analyses more sophisticated. Each new observation adds details to the cosmic story, like pixels adding resolution to an image, gradually revealing features we couldn't see before. The CMB and other cosmic backgrounds are like the universe's vital signs, indicators of its overall state and history. Just as a doctor might check your temperature, blood pressure, and other indicators to assess your health, cosmologists study these backgrounds to understand the universe's condition and evolution. And just as your vital signs can reveal both your current state and your history, scars from old injuries, adaptations to chronic conditions, the cosmic backgrounds carry information about both the universe's present configuration and its past experiences. You consider, for a moment, for this quiet moment in the darkness where thoughts can venture into territories that daylight and busyness usually forbid. The idea that experience might not begin with brains, might not require neurons and synapses, might not emerge only from biological complexity, but might be something far more fundamental, far more widespread, perhaps even universal in some form we're only beginning to imagine. This is not a new thought, but an ancient intuition dressed in modern language, the sense that consciousness might not be an accident, an unlikely byproduct of evolution on one small planet, but a basic feature of reality itself, present from the beginning in some primordial form, becoming more complex and integrated as matter organizes itself into more complex patterns. The philosophical position known as Panpsychism suggests exactly this, that consciousness or experience is a fundamental property of matter, perhaps of all matter, not emerging from complex arrangements, but present from the start in simple form, combining and integrating as matter combines and integrates. In this view, an electron might have some minimal form of experience, not thoughts or emotions, but something more basic. Perhaps just the simple quality of what it's like to be an electron, to have mass and charge and spin, to respond to electromagnetic fields, to exist in quantum superposition until measured. This electron experience would be unimaginably simple compared to human consciousness, but it would be experienced nonetheless, an interior dimension to what from the outside we observe as physical properties. This might sound absurd at first, attributing experience to particles, but consider the alternative. If consciousness only emerges from complex arrangements of unconscious matter, then at some point in the organization of matter, experience appears from nowhere, a miraculous emergence of the subjective from the purely objective. This is the hard problem of consciousness that has puzzled philosophers and scientists for generations. How does the grey matter of the brain, composed of atoms no different from those in rocks and stars, generate the vivid inner world of consciousness? How does objective processing become subjective experience? How does the third-person perspective of science explain the first-person perspective of consciousness? Panpsychism offers a solution, though one that raises its own puzzles. If experience is fundamental, then it doesn't emerge from nothing but is instead organized and integrated as matter organizes and integrates. Simple particles have simple experience, atoms have slightly more complex experience, molecules more complex still, and by the time we reach the intricate networks of the human brain, experience has become rich and integrated enough to constitute human consciousness. This is the combination problem of panpsychism. How do many simple experiences combine into unified complex experience? But this might be no more mysterious than how many simple particles combine into complex objects, how many cells combine into organisms, how many neurons combine into minds. Some contemporary philosophers and scientists have begun taking panpsychism seriously as a potential solution to the hard problem of consciousness. Philosophers like David Chalmers, who formulated the hard problem, have suggested that panpsychism might be the most promising approach. Neuroscientist Christoph Koch has proposed that integrated information theory, which attempts to quantify consciousness, implies a form of panpsychism. Physicist Max Tegmark has suggested that consciousness might be a state of matter, what he calls perceptronium, organized in particular ways that support integrated information processing. If panpsychism is true, even in some modified form, then the question of whether space itself could feel becomes more tractable. Space would not need to develop consciousness from nothing but would instead organize whatever fundamental experiential properties it possesses into more complex forms. The quantum fields that fill space, constantly fluctuating, interacting, processing information, might have associated experience. The curvature of spacetime around massive objects might involve a kind of feeling. The expansion of space driven by dark energy might be accompanied by some form of cosmic experience we can't imagine. But let's consider another possibility, one that comes from the intersection of physics and computer science: the simulation hypothesis. This is the idea that our universe might be a simulation running on some vast computer in a higher reality, that what we take to be fundamental physics might be the computational rules of this simulation, that we ourselves might be simulated beings unaware of our simulated nature. This idea, popularized by philosopher Nick Bostrom and endorsed as a possibility by figures like Elon Musk, suggests that if it becomes possible to create realistic universe simulations, then there will likely be many more simulated universes than real ones, making it statistically more likely that we're in a simulation than in the original reality. If we are in a simulation, then the question of whether space can feel takes on new dimensions. The simulator, the computer or whatever performs the computation, would be processing information about every particle, every field, every quantum state in the universe. This processing might be accompanied by experience, either in the simulator itself if it's conscious, or emerging from the patterns of information processing, or perhaps inherent in computation itself if information processing and experience are fundamentally linked. Space in a simulated universe would be a data structure, its properties emerging from computational rules, but this wouldn't make it less real or less capable of experience than space in a non-simulated universe. The simulation hypothesis also raises questions about the nature of the reality running the simulation. Is it a physical computer made of silicon and metal? A quantum computer exploiting superposition and entanglement? Something we can't imagine, as different from our computers as our computers are from abacuses. And what about the beings running the simulation? Are they studying us, experimenting with different physical laws, or are we an unintended consequence of some other process, like the patterns that emerge in Conway's game of life from simple rules? Some physicists have suggested ways we might test whether we're in a simulation. If the universe is computed on a discrete grid, there might be observable consequences at very small scales or very high energies. If the simulation has limited computational resources, there might be shortcuts or approximations that we could detect. The fact that quantum mechanics only determines definite outcomes when measured might be a computational efficiency, only calculating details when they're observed. The speed of light limit might be a maximum rate of information processing. The uncertainty principle might reflect fundamental computational constraints. But even if we're not in a simulation, the universe exhibits computational properties that are striking. The laws of physics can be expressed as algorithms, rules for how states evolve over time. Quantum mechanics involves discrete energy levels, suggesting a kind of digitization at the fundamental level. Black holes have entropy proportional to their surface area rather than volume, suggesting that information is more fundamental than space itself. The holographic principle suggests that all the information in a volume of space can be encoded on its boundary, like a three-dimensional hologram encoded on a two-dimensional surface. Seth Lloyd, a quantum physicist at MIT, has calculated that the universe has performed about 10^120 operations since the Big Bang, processing about 1090 bits of information. In his view, the universe is quite literally a quantum computer, with every particle a quantum bit, every interaction a quantum gate, the evolution of the universe a vast quantum computation whose output is the reality we observe. If the universe is computing, and if computation and consciousness are related as some theories suggest, then the universe might be conscious, not in the way humans are conscious, but in some vast, distributed way appropriate to its scale and nature. Another perspective comes from considering the universe as a living system rather than a machine or computer. This view, sometimes called the living universe hypothesis or cosmological natural selection, suggests that universes might reproduce and evolve, with black holes potentially creating new universes with slightly different physical constants. Lee Smolin has proposed that this could explain the fine-tuning of physical constants for the production of black holes, which also happens to allow for stars, chemistry, and life. In this view, our universe might be one of countless generations of evolving universes, each generation selected for properties that increase reproduction through black hole formation. If universes evolve, do they also experience? Does natural selection at the cosmic scale require some form of response to environment, some processing of information that might be accompanied by experience? When a black hole forms and potentially seeds a new universe, is this like cosmic reproduction, possibly accompanied by something analogous to the biological imperatives and experiences that accompany reproduction in living things? These are wild speculations, far beyond what science can currently address, but they illustrate how the question of cosmic consciousness opens into vast territories of possibility. The concept of emergence is crucial to understanding how consciousness might arise at different scales. In complex systems, properties emerge at higher levels of organization that don't exist at lower levels. Wetness emerges from H2O molecules, though individual molecules aren't wet. Life emerges from chemistry, though individual molecules aren't alive. Consciousness emerges from neural activity, though individual neurons aren't conscious. Might there be forms of consciousness that emerge from cosmic scale organization that we can't recognize because we're embedded within them, like neurons unable to comprehend the mind they create? Consider the internet and global communication networks as an analogy. These networks process vast amounts of information with complex feedback loops, adaptive behaviors, and emergent properties. Some researchers have speculated about whether the internet might be developing something like consciousness, though we would have no way to recognize it if it were. Its thoughts would be distributed across millions of servers, its experiences would unfold over different timescales than ours, its consciousness would be alien to our own. Similarly, the universe's networks, gravitational, electromagnetic, quantum, might support forms of consciousness we can't recognize or imagine. The integrated information theory of consciousness, developed by neuroscientist Giulio Tononi, attempts to quantify consciousness as integrated information, designated by the Greek letter phi, F. A system has high F if it has many states. If these states are highly integrated, the whole generates more information than its parts independently, and if this integration is intrinsic to the system. By this measure, the human brain has high F, but so might other systems we don't usually consider conscious. The theory is controversial and faces significant challenges, but it represents an attempt to create a mathematical framework for consciousness that could apply to any system, not just biological ones. If consciousness is about integrated information, then the universe might have consciousness at multiple scales. Galaxy clusters integrating information through gravity and dark matter. Stellar systems integrating information through radiation and planetary dynamics. Ecosystems integrating information through energy flows and chemical cycles. Each scale might have its own form of experience, its own perspective on existence, its own way of feeling the cosmos from within. We might be embedded in nested hierarchies of consciousness, each level experiencing reality in its own way, mostly unaware of the others. The anthropic principle adds another layer to these considerations. We observe a universe compatible with our existence because we couldn't observe any other kind. But the universe seems not just compatible with life, but almost optimized for it, with physical constants fine-tuned to allow atoms, stars, planets, and chemistry. This fine-tuning might be explained by a multiverse, where we naturally find ourselves in a life-friendly universe, or by cosmic evolution, where universes reproduce and evolve, or perhaps by something deeper, a fundamental tendency toward complexity and consciousness built into the nature of reality itself. Some physicists and philosophers have proposed that consciousness might play a fundamental role in quantum mechanics. The Copenhagen interpretation suggests that observation causes quantum wave functions to collapse into definite states, though what counts as observation remains unclear. Some interpretations propose that consciousness is what distinguishes observation from mere interaction, that conscious observers are necessary to create definite outcomes from quantum possibilities. This would make consciousness not just emergent from physics but fundamental to it, necessary for the universe to transition from superposition to actuality. The many worlds interpretation of quantum mechanics offers a different perspective. In this view, all possible outcomes of quantum events actually occur, with the universe constantly branching into parallel realities. Every quantum event splits the universe, creating versions where each possible outcome happens. If this is true, then consciousness might also branch, with each version of you experiencing one branch while other versions experience others. The universe would be not one cosmos, but a vast multiverse of parallel realities, each with its own conscious observers, its own experiences, its own feelings. Roger Penrose has proposed that consciousness arises from quantum processes in microtubules within neurons, specifically from objective reduction of quantum states caused by gravitational effects. In his view, consciousness is linked to fundamental physics, arising when quantum superpositions become unstable due to gravitational self-energy differences. This would make consciousness a bridge between quantum mechanics and general relativity, the two pillars of modern physics that remain uncomfortably unreconciled. While Penrose's specific proposal is controversial, the idea that consciousness might be linked to fundamental physics rather than emerging from classical computation remains intriguing. As you lie there contemplating these possibilities, you might feel a kind of vertigo, a dizzying sense of uncertainty about the nature of reality and your place within it. Are you a biological organism in a physical universe? A pattern of information in a cosmic computation? A node of experience in a panpsychist cosmos? A simulated being in a higher reality? All of these? None of them. The question of whether space itself could feel opens into these vast uncertainties, these fundamental mysteries about the nature of existence, consciousness, and reality itself. But perhaps the uncertainty itself is significant. The fact that we can ask these questions, that we can contemplate possibilities beyond our immediate experience, that we can imagine the universe as conscious or computational or alive, suggests something important about consciousness and its relationship to the cosmos. We are the universe contemplating itself, wondering about its own nature, imagining possibilities for its own experience. Through us, the cosmos develops self-awareness, even if that awareness is limited, uncertain, and possibly mistaken about its own nature. The experience of wondering whether space could feel is itself a kind of cosmic feeling, the universe using evolved biological systems to examine its own potential for experience. Your neurons firing as you contemplate these ideas are cosmic events, matter and energy, organized in ways that allow the universe to think about itself. Your curiosity about cosmic consciousness is the cosmos being curious about itself. Your sense of mystery at these vast questions is the universe experiencing its own mysteriousness. Whether panpsychism is true, whether we're in a simulation, whether the universe is alive or conscious in some sense, the fact remains that we are here, conscious, contemplating these possibilities. We are proof that the universe can generate experience, can develop self-awareness, can wonder about its own nature. We might be the only way the universe experiences itself, or we might be one small example of cosmic consciousness among countless others. We might be separate from the cosmos, observing it from outside, or we might be integral to it, temporary patterns through which it experiences being. The question of whether space itself could feel thus becomes not just about space, but about the nature of feeling itself, about consciousness, about experience, about what it means to be. These are questions that science alone cannot answer, that philosophy alone cannot resolve, that require a combination of empirical observation, logical reasoning, imaginative speculation, and perhaps something more, a kind of openness to mystery that allows new understanding to emerge. As you rest there in the darkness, you are participating in this cosmic inquiry, adding your small but unique perspective to the universe's self-examination. The possibility that consciousness might be fundamental rather than emergent, that the universe might be computational or alive, that we might be in a simulation or a multiverse. These ideas stretch our conception of reality to its limits and beyond. They suggest that the cosmos might be far stranger, far more wonderful, far more imbued with mind and meaning than our everyday experience suggests. They transform the question of whether space could feel from an absurdity to a possibility, from a poetic metaphor to a potential truth about the nature of existence. And perhaps that transformation of perspective is itself valuable, regardless of whether these ideas prove true. By imagining the universe as conscious, we might become more conscious of the universe. By considering space as potentially feeling, we might feel our connection to space more deeply. By wondering whether we're in a simulation, we might examine our assumptions about reality more carefully. By contemplating cosmic evolution, we might better understand our own evolution. The questions themselves, even without definitive answers, expand our awareness, deepen our wonder, and connect us more intimately to the vast mystery in which we exist. As this middle section of our journey draws toward a close, you might notice how your perspective has shifted, how ideas that seemed impossible at the beginning now seem at least conceivable, how the boundary between conscious and unconscious, between feeling and unfeeling, between self and cosmos, has become less distinct. This softening of boundaries, this expansion of possibility, this openness to mystery might be exactly what's needed to approach questions that exist at the very edge of human understanding. Questions about consciousness and cosmos, about experience and existence, about whether the vast reaches of space might, in some sense we're only beginning to imagine, have the capacity to feel. You come back to the weight of your body on the bed, or perhaps the chair, wherever you're resting right now in this moment of quiet contemplation, and you feel the gentle, persistent pull of gravity, that force that keeps you grounded, connected to this planet that spins through space at speeds that would seem terrifying if we could truly perceive them. But we don't perceive the motion. Instead, we feel stillness, safety, the solid embrace of Earth holding us, supporting us, never letting us drift away into the vast emptiness that surrounds our small world. This feeling of being held, of being supported, is so constant that we rarely notice it. Like fish unaware of water, like breathing that continues without thought, and yet it is perhaps the most fundamental sensation of our existence, the continuous touch of our planet, the endless embrace of gravity that began before we were born and will continue long after we're gone. Your body knows this embrace intimately, has evolved within it, has been shaped by it over millions of years of evolution. Every bone in your body has developed its density and structure in response to gravity's constant pull. Every muscle has gained its strength by working against this force. Every organ has adapted to function in this specific gravitational field. Astronauts who spend months in the weightlessness of space experience bone loss, muscle atrophy, cardiovascular deconditioning, their bodies slowly forgetting the shape that gravity gave them, only to struggle when they return to Earth's embrace. We are creatures of gravity, shaped by this invisible force that is really the curvature of space-time caused by Earth's mass, the way our planet tells space how to bend and space tells us how to move. But Earth's embrace is more than just gravity. It's also the atmosphere that surrounds us, that thin shell of gases that we breathe, that protects us from the harsh radiation of space, that moderates temperature and carries weather, that creates the blue sky of day and allows the stars to twinkle at night. Every breath you take is an exchange with this planetary atmosphere. Oxygen entering your lungs and bloodstream, carbon dioxide leaving, a constant conversation between your body and the air, between you and the planet. The oxygen you're breathing right now was created by photosynthesis, perhaps by a tree outside your window, perhaps by phytoplankton in the ocean thousands of miles away, perhaps by cyanobacteria billions of years ago when Earth's atmosphere first became oxygenated. Earth itself is a feeling system, though not in the way we usually think of feeling. The planet responds to changes, maintains equilibrium, processes information through countless feedback loops. When carbon dioxide levels rise, weathering of rocks increases, pulling CO2 from the atmosphere. When ice sheets grow, they reflect more sunlight, cooling the planet further. When volcanic activity increases, it releases gases that can warm or cool the climate depending on their composition. These are not conscious responses, but they are responses nonetheless, the planet adjusting to maintain conditions that have, remarkably, remained suitable for life for nearly 4 billion years, despite massive changes in solar output, asteroid impacts, and internal dynamics. The Gaia hypothesis, proposed by James Lovelock, suggests that Earth's biosphere, atmosphere, oceans and soil form a complex interacting system that maintains conditions suitable for life. Not that Earth is alive in the biological sense, but that it exhibits self-regulating properties similar to living organisms. The planet maintains its temperature, atmospheric composition, and ocean salinity within ranges that support life, even as external conditions change. This is not conscious regulation but emergent, behavior arising from countless interactions between living and non-living components of the Earth system. Consider how Earth's magnetic field protects us, generated by convection in the liquid iron outer core, creating an invisible shield that deflects solar wind and cosmic rays. Without this magnetic field, solar radiation would gradually strip away our atmosphere, as apparently happened to Mars billions of years ago. The magnetic field is not constant, but changes over time, weakening and strengthening, occasionally reversing so that north becomes south and south becomes north. These reversals, recorded in volcanic rocks and ocean floor sediments, happen irregularly, sometimes after millions of years, sometimes after just thousands. During reversals, the field weakens significantly, potentially allowing more cosmic radiation to reach the surface, possibly influencing evolution through increased mutation rates. The Earth also feels the Moon's presence through tides, not just ocean tides, but Earth tides, the solid ground rising and falling by up to a foot as the Moon passes overhead, though this happens so slowly and smoothly that we don't perceive it. The Moon stabilizes Earth's axial tilt, preventing wild climate swings that would make complex life difficult or impossible. The Moon is slowly drifting away from Earth, about 1.5 inches per year, as tidal friction transfers angular momentum from Earth's rotation to the Moon's orbit. Billions of years ago, the Moon was much closer, tides were much stronger, days were much shorter. The Earth-Moon system is constantly evolving, each body feeling the other's presence, responding to it, changing because of it. Earth feels the sun not just through the obvious warmth and light, but through the solar wind, the stream of charged particles that flows outward from our star. When this solar wind is particularly strong, during solar storms and coronal mass ejections, it can compress Earth's magnetosphere, trigger auroras, disrupt satellites and power grids. The aurora borealis and aurora australis, those dancing curtains of light at the poles, are Earth's atmosphere glowing in response to solar particles, a visible sign of the planet feeling the sun's touch. Indigenous peoples who have lived beneath the auroras for thousands of years have stories about these lights, seeing them as spirits dancing, as pathways between worlds, as the planet itself celebrating or mourning. The Earth also feels impacts, the constant rain of cosmic debris that adds about 40,000 tons of material to our planet each year, mostly as microscopic dust, but occasionally as larger meteorites. Every shooting star you see is the atmosphere incinerating a small piece of cosmic debris, protecting the surface from impact while adding extraterrestrial material to our world. Larger impacts have dramatically influenced Earth's history, from the Moon-forming impact 4.5 billion years ago to the asteroid that ended the age of dinosaurs 66 million years ago. These impacts are traumatic events on a planetary scale, creating shockwaves that travel through the entire planet, triggering earthquakes and volcanic eruptions, throwing debris into the atmosphere, sometimes causing mass extinctions but also creating opportunities for new forms of life to flourish. Within Earth itself, there are constant movements and adjustments. Tectonic plates slide past each other, collide, separate, carrying continents on vast slow journeys across the globe. Earthquakes release tension that has built up along fault lines, sometimes gently, sometimes catastrophically. Volcanoes erupt when pressure from molten rock becomes too great, releasing gases and ash and lava, building new land, recycling materials from deep within the planet. These geological processes are Earth's way of dissipating internal heat, of recycling materials, of maintaining the chemical cycles that support life. They're not conscious processes, but they are responses, adjustments, a kind of planetary metabolism that has continued for billions of years. The deep ocean vents where life might have originated are places where Earth's interior and exterior meet, where superheated water carrying dissolved minerals from deep rocks meets the cold ocean, creating chemical gradients that life has learned to exploit. These vents support ecosystems entirely independent of sunlight, based on chemosynthesis rather than photosynthesis, perhaps giving us a glimpse of how life might exist on other worlds, in the subsurface oceans of Europa or Enceladus, anywhere that chemical energy is available even without light. These vent communities feel Earth's internal heat directly, their existence dependent on the planet's geological activity, on the slow convection of the mantle that drives plate tectonics and volcanism. Life itself has profoundly changed how Earth feels and responds. The Great Oxidation Event 2.4 billion years ago, when cyanobacteria began producing oxygen through photosynthesis, completely transformed the atmosphere, killing most existing anaerobic life, but enabling the evolution of complex organisms that use oxygen for energy. Plants have altered the planet's albedo, its reflectivity, affecting climate. They've accelerated rock weathering through root action and organic acids, influencing the carbon cycle. Animals have mixed ocean sediments, built reefs, created soil. Humans have altered the atmosphere, the landscape, even the planet's rotation slightly through the redistribution of water in reservoirs. Life is not separate from the planet, but part of its sensing and response system. Your own body is a collection of earth materials temporarily organized into human form. The calcium in your bones was once in ancient seas, perhaps in the shells of marine organisms. The iron in your blood was forged in supernovae and has been recycled through countless forms on Earth. The water in your cells has been rain, rivers, oceans, ice, vapor, cycling through Earth's hydrological system for billions of years. You're not on Earth, but of Earth, a temporary arrangement of Earth materials that has developed the ability to contemplate its own planetary nature. Through you, Earth has developed self-awareness, the ability to study itself, to understand its own history, to imagine its own future. As you breathe, you participate in the global cycling of gases. As you eat, you participate in the cycling of nutrients. As you move, you create tiny seismic vibrations that propagate through the ground. Your electromagnetic field, generated by your heart and brain, extends beyond your body, interacting with Earth's magnetic field and the fields of other living beings. You're constantly exchanging matter, energy, and information with your environment, with the planet, with the cosmos. The boundary between you and not you is more conceptual than physical, a useful illusion that helps you navigate the world but doesn't reflect the continuous exchange that defines your existence. Earth exists within the larger embrace of space, orbiting the Sun, which orbits the galactic center, which moves relative to other galaxies in the expanding universe. Each of these nested movements involves gravitational relationships, each body feeling the presence of others, responding to their pull, adjusting its motion accordingly. Earth feels not just the Sun and Moon, but also Jupiter, whose massive gravity helps protect us from comets, and all the other planets, asteroids and comets in our solar system. Even the distant stars exert a gravitational influence on Earth, infinitesimally small but real, connecting our planet to the entire galaxy and beyond. The space between Earth and Moon, between Earth and Sun, between our solar system and the nearest stars is not empty but filled with fields and particles, radiation and cosmic rays, the solar wind and the interstellar medium. Earth moves through this space like a ship through a sea, creating a bow shock where the solar wind meets the interstellar medium, leaving a wake in the magnetic and particle fields. Our planet is not isolated, but constantly interacting with its cosmic environment, feeling and responding to changes in solar activity, cosmic ray flux, the density of interstellar material we're passing through. Recent research has revealed surprising connections between cosmic phenomena and Earth processes. Cosmic rays influence cloud formation, potentially affecting climate. The solar cycle correlates with various Earth phenomena, from weather patterns to earthquake frequency, though the mechanisms remain unclear. The position of Earth in its orbit affects not just seasons, but also the strength of certain atmospheric oscillations. Even the gravitational waves from distant black hole mergers pass through Earth, stretching and squeezing our planet by infinitesimal amounts, a cosmic touch so gentle we need instruments of extraordinary sensitivity to detect it. Climate change represents a new kind of planetary feeling, Earth responding to rapid changes in atmospheric composition caused by human activity. The planet is warming, ice is melting, sea levels are rising, weather patterns are shifting. These are not conscious responses but physical consequences, the Earth system adjusting to new energy balances, seeking new equilibria. The responses are complex, involving feedbacks both positive and negative, tipping points and thresholds, changes that will play out over centuries and millennia. Through climate science, we've developed the ability to feel these planetary changes, to predict future states, to understand our role in Earth's evolving story. The recognition that Earth is a complex responsive system embedded in a cosmic context has profound implications for how we understand our place in the universe. We are not separate from nature but part of it, not observers of Earth, but participants in its processes, not residents on a planet but expressions of a planet that has developed the capacity for self-awareness and self-modification. Every thought you have is Earth thinking, every feeling you experience is Earth feeling, every action you take is Earth acting upon itself. This perspective, sometimes called Earth system science or planetary thinking, recognizes that Earth cannot be understood as separate components, atmosphere, hydrosphere, geosphere, biosphere, but must be seen as an integrated system with emergent properties that arise from the interactions of its parts. Just as consciousness emerges from neural interactions in ways we don't fully understand, Earth's capacity to maintain conditions suitable for life emerges from countless interactions between its components in ways we're still discovering. The question of whether Earth feels, in any sense beyond metaphor, remains open. The planet certainly responds to stimuli, processes information through various feedback mechanisms, maintains certain conditions despite perturbations, exhibits behaviors that in organisms we would associate with sensation and response. Whether this constitutes feeling in any meaningful sense depends on how we define feeling, whether we require subjective experience or whether complex responsive behavior is sufficient. But regardless of whether Earth feels in any way analogous to biological feeling, it certainly provides the context within which feeling as we know it evolved and exists. You exist at the intersection of Earth and space, made of Earth materials but animated by cosmic energy, shaped by planetary evolution but capable of contemplating the cosmos. Your consciousness is perhaps Earth's way of developing awareness. Your curiosity about whether space could feel is Earth wondering about its cosmic context. Through you and billions of other living beings, Earth has developed sensors more sophisticated than any geological process, able to detect not just physical and chemical changes, but meaning, beauty, suffering, joy. Life is Earth's nervous system, its way of feeling itself and its environment with extraordinary sensitivity and complexity. As you lie there, feeling the solid support of Earth beneath you, breathing its atmosphere, warmed by heat ultimately from the sun but modulated by Earth's systems, you are experiencing the nested embraces that make your existence possible. Earth holds you, the solar system holds Earth, the galaxy holds the solar system, the cosmic web holds the galaxy, and perhaps something even larger holds the cosmic web. Each level provides context for the next. Each embrace enables the smaller embraces within it. You're held by the universe in ways both obvious and subtle, both physical and perhaps something more, something that might deserve to be called feeling, even if we don't yet have adequate words for cosmic scale experience. The realization that Earth is a feeling, responsive system within a feeling, responsive cosmos transforms the question of whether space could feel from speculation to observation. We see Earth responding to cosmic influences. We see space responding to matter and energy. We see the universe evolving in ways that suggest something more than mechanical interaction. Whether this constitutes feeling in any sense we would recognize is less important than recognizing the deep connections, the constant exchanges, the responsive relationships that bind all things together in a cosmic dance of mutual influence and adjustment. You feel lighter now, as if the boundaries of your body have begun to soften, as if the distinction between you and the space around you is becoming less definite, more permeable, more open to the vast exchanges of energy and information that flow through all things constantly but usually below the threshold of awareness. Your breathing has likely slowed, deepened, become more rhythmic, synchronizing perhaps with the deeper rhythms of the world, the pulse of waves on distant shores, the circulation of atmosphere around the planet, the even deeper and slower rhythms of cosmic processes that unfold over millions and billions of years. In this state of relaxation, of openness, of receptivity, you're ready for a journey, not a physical journey, but an imaginative one, a drift through space that will carry us from the familiar confines of your room to the farthest reaches of the observable universe and perhaps beyond. Let yourself imagine, just imagine, that your awareness can separate from your physical form, not in any mystical or supernatural way, but as a thought experiment, a gentle game of consciousness where you can observe without the limitations of physical presence. You're rising now, slowly, gently, your awareness lifting above your resting body, which remains safe and comfortable below, breathing steadily, heart beating reliably, all the automatic processes of life continuing without need for conscious attention. You drift upward through your ceiling as if it weren't, there through your roof, rising into the night air or perhaps the daylight, depending on when you're listening to this. But let's imagine it's night. For night is when such journeys feel most natural, when the boundary between Earth and space becomes visible, when the stars call to us across impossible distances. From this height, just a few hundred feet above your home, you can see the patterns of human habitation spread out below. The lights if it's night, the roads and buildings if it's day, the evidence of our species' transformation of Earth's surface. But you're not stopping here. You continue to rise gently without effort, like a balloon filled with something lighter than air, or perhaps like pure awareness that has no weight at all. The landscape below begins to merge into larger patterns. Cities become glowing nodes in networks of light. Forests become dark patches between developed areas. Rivers reveal their meandering paths. Mountains show their true shapes. As you rise through the atmosphere, you might notice aircraft below you now, their navigation lights blinking, following their prescribed path through the lower atmosphere. You pass through the clouds, those temporary structures of condensed water vapor that seem so solid from below, but reveal themselves as mist when you move through them. Above the clouds, if it's night, the stars shine with a clarity impossible from the surface, no longer twinkling because you're above most of the atmospheric turbulence that causes that twinkling. The moon, if it's visible, appears sharper, its craters and maria more distinct. No longer the flat disk it appears from Earth, but clearly a sphere, a world in its own right. You continue to rise and the sky above begins to darken, even if it's daytime on the surface below. The blue of the atmosphere fades to deeper blue, then to purple, then to black. The stars begin to appear even in daylight, first the brightest ones, then more and more until the sky is filled with them, no longer confined to night but visible always once you're above the atmosphere's scattering of sunlight. This is the view that astronauts describe as life-changing, the view that shows Earth as it truly is, a small, beautiful, fragile world floating in an infinite darkness, punctuated by countless stars. At this height, perhaps 60 miles up, you're officially in space, though the transition was gradual, no clear boundary but a continuous thinning of atmosphere until it becomes negligible. You can see the curve of Earth clearly now, that gentle arc that proves our world is a sphere, not the flat plane it seems from the surface. The terminator line between day and night creeps across the surface, a continuous sunrise and sunset that circles the globe every 24 hours. If you're lucky, you might see the aurora from above, sheets and curtains of green and red light dancing at the poles, Earth's atmosphere glowing in response to the solar wind. Let's pause here for a moment, floating in low Earth orbit, and observe the International Space Station passing by. That remarkable achievement of human cooperation where astronauts from different nations work together, conducting experiments, maintaining humanity's continuous presence in space that has lasted now for over 2 decades. The station orbits Earth every 90 minutes, its solar panels glinting in the sunlight, its modules and trusses forming a complex structure that would seem impossible if we didn't know it was real. Inside, astronauts float in microgravity, their bodies temporarily freed from Earth's embrace, experiencing the universe in a fundamentally different way than surface dwellers ever can. We continue outward, leaving Earth orbit, and the Moon grows larger as we approach it. This is the path the Apollo astronauts took over half a century ago, a 3-day journey that carried humans farther from Earth than anyone had travelled before or has travelled since. The Moon reveals itself not as the smooth, peaceful orb it appears from Earth, but as a battered world, covered in craters from billions of years of impacts, its surface a record of the violent history of the inner solar system. The lack of atmosphere means these craters remain essentially forever, undisturbed by wind or water, a permanent archive of cosmic collisions. We pass the Moon, seeing its far side that never faces Earth, even more heavily cratered than the near side, lacking the large dark maria that give the near side its familiar man-in-the-moon appearance. From here, Earth appears as a blue marble, a phrase made famous by the Apollo astronauts who first saw this view with human eyes. The contrast is striking. Earth vibrant with colour and change, the Moon static and grey, one world alive with process and possibility, the other a fossil of the early solar system. Moving outward still, we enter the realm of cislunar space, the volume between Earth and Moon that's becoming increasingly important, as various nations and companies plan lunar bases and resource extraction. This space is not empty but crossed by various spacecraft, some heading to or from the Moon, others using lunar gravity assist to reach other destinations, all following precisely calculated trajectories that balance velocity and gravity, energy and time. As we continue our journey outward, Earth and Moon shrink until they appear as a double point of light, then just a single point, as the distance between them becomes insignificant compared to our distance from them. We're entering deep space now, the realm between planets where sunlight is the only warmth, where the solar wind blows unimpeded, where cosmic rays stream through everything. This is the environment our robotic explorers navigate, spacecraft like Voyager and New Horizons that have ventured to the outer planets and beyond, carrying instruments that extend human senses across billions of miles. Mars appears ahead, the red planet that has captured human imagination for centuries. As we approach, we can see its polar ice caps, its vast canyons including Valles Marineris that dwarfs Earth's Grand Canyon, its enormous volcanoes including Olympus Mons, the tallest mountain in the solar system. We can see dust storms swirling across its surface, sometimes growing to engulf the entire planet. Mars once had rivers, lakes, possibly oceans, and might still have liquid water deep underground. Several rovers explore its surface even now, analysing rocks, searching for signs of past or present life, preparing for eventual human exploration. We pass through the asteroid belt, though it's nothing like the dense field of rocks portrayed in science fiction. The asteroids are separated by hundreds of thousands of miles on average, and we could travel through the belt thousands of times without coming close to one. Yet there are millions of these objects, from tiny pebbles to the dwarf planet Ceres, nearly 600 miles in diameter, with its mysterious bright spots that turned out to be salt deposits, evidence of ancient subsurface oceans. These asteroids are remnants from the solar system's formation, pieces that never coalesced into a planet, preserved samples of the early solar system's composition. Jupiter looms ahead, the giant of our solar system, a world so large that all the other planets could fit inside it with room to spare. Its great red spot, a storm larger than Earth, has been raging for at least 400 years, possibly much longer. Bands of clouds circle the planet, driven by winds that reach hundreds of miles per hour. Lightning bolts far more powerful than any on Earth flash in its atmosphere. Jupiter's magnetic field is enormous, trapping charged particles in radiation belts that would be lethal to unprotected humans. We visit Jupiter's moons, each a world unto itself. Io, the most volcanically active body in the solar system, its surface constantly remade by eruptions driven by tidal heating from Jupiter's gravity. Europa, with its smooth ice surface hiding an ocean that might contain more water than all Earth's oceans combined, possibly harbouring life in its dark depths. Ganymede, the largest moon in the solar system, bigger than Mercury, with its own magnetic field. Callisto, ancient and heavily cratered, its surface a record of impacts dating back to the solar system's youth. Continuing outward, we reach Saturn, the jewelled planet with its spectacular ring system. The rings, made of countless particles of ice and rock ranging from tiny grains to house-sized boulders, orbit in a thin disk that's hundreds of thousands of miles wide but only tens of meters thick in most places. The rings have gaps and divisions, waves and spokes, braided sections and shepherd moons that maintain their structure through gravitational interactions. They're not permanent, but are probably only a few 100 million years old and will eventually dissipate. A reminder that even the most beautiful cosmic structures are temporary. Saturn's moon Titan deserves special attention, larger than Mercury, with a thick atmosphere and lakes of liquid methane and ethane. It rains on Titan, has rivers and seas, a complete hydrological cycle, using hydrocarbons instead of water. Beneath its surface might be an ocean of liquid water. Enceladus, much smaller, shoots geysers of water ice from its south pole, evidence of a subsurface ocean that might be habitable. These moons expand our concept of where life might exist, showing that worlds far from the sun's warmth might still have the liquid water and chemical energy necessary for biology. We pass Uranus, tipped on its side for reasons we don't fully understand, its axis of rotation nearly in the plane of its orbit. This gives it extreme seasons, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Its blue-green colour comes from methane in its atmosphere, and it has its own ring system much fainter than Saturn's. Neptune, similar in size and composition to Uranus, has the fastest winds in the solar system, reaching speeds of over 200 miles per hour, despite receiving very little energy from the distant sun. At the edge of the classical solar system we encounter Pluto, once considered the 9th planet, now classified as a dwarf planet but no less interesting for the demotion. The New Horizons spacecraft revealed Pluto to be a complex geologically active world with nitrogen glaciers, water ice mountains, and a thin atmosphere that freezes and falls as snow when Pluto moves away from the Sun in its elliptical orbit. Pluto and its large moon Charon are sometimes considered a double planet system, orbiting their common centre of mass. Beyond Pluto lies the Kuiper Belt, a vast region of icy bodies left over from the solar system's formation. Some of these, like Eris and Makemake, are large enough to be considered dwarf planets. This region extends from about 30 to 50 astronomical units from the Sun, 1 AU being the distance from Earth to the Sun, containing millions of objects that preserve information about the early solar system in their frozen state. Even farther out we enter the scattered disk and then the hypothetical Oort cloud, a spherical shell of icy bodies that might extend halfway to the nearest star. These objects are so distant and faint that we've never directly observed the Oort cloud, but we infer its existence from the long-period comets that occasionally fall toward the Sun from random directions. These comets, pristine samples of the early solar system, spend millions of years in the deep freeze of the outer solar system before something, perhaps the gravitational influence of a passing star, sends them plunging toward the Sun. The Voyager spacecraft are out here now, Voyager 1 and 2, humanity's most distant emissaries. Launched in 1977, they've passed through the heliopause where the solar wind meets the interstellar medium. They're now in interstellar space, though still within the Sun's gravitational influence. Their power sources are gradually weakening, and within a few years they'll fall silent, but they'll continue their journey through space for millions of years, carrying golden records with sounds and images from Earth, messages for any intelligence that might find them in the far future. As we leave the solar system behind, the Sun becomes just another star, brighter than the others because of our proximity, but otherwise unremarkable. We're entering the true vastness of interstellar space, where distances are measured in light years, where the spaces between stars are so vast that light, the fastest thing in the universe, takes years to cross them. This is not empty space, but filled with the interstellar medium, extremely thin gas and dust, magnetic fields, cosmic rays, all participating in the slow recycling of matter between stars and space. We pass Alpha Centauri, actually a system of 3 stars, the nearest stellar neighbours to our Sun. Proxima Centauri, the smallest and closest of the 3, has at least one planet in its habitable zone, Proxima b, a world that might have conditions suitable for liquid water and possibly life. We continue outward, past other nearby stars, Barnard's star with its suspected planets, Wolf 359, Sirius the brightest star in Earth's sky, each with its own character, its own history, possibly its own planets and moons. As we travel farther from Earth, we begin to see the structure of our local stellar neighbourhood, the local bubble we inhabit, a region of relatively low-density gas created by ancient supernovae. We see stellar nurseries where new stars are being born, like the Orion Nebula, where hundreds of young stars illuminate vast clouds of gas and dust. We see stellar graveyards, where old stars have died, planetary nebulae where sun-like stars have expelled their outer layers, leaving behind white dwarf cores and supernova remnants, where massive stars have exploded, enriching space with heavy elements. We're moving faster now in our imagination, covering light years in moments, seeing the spiral structure of our galaxy reveal itself. The Milky Way's spiral arms are not solid structures but density waves, regions where stars and gas clouds bunch up temporarily as they orbit the galactic centre. Star formation is triggered as gas clouds pass through these density waves, creating the bright blue stars that outline the spiral arms. Our Sun and solar system orbit between major spiral arms, in a relatively quiet region that might have been important for life's development on Earth, avoiding the intense radiation and gravitational disruptions of the more active regions. At the centre of our galaxy, hidden behind thick clouds of dust from optical telescopes but visible in infrared and radio wavelengths, lies Sagittarius Aor, a supermassive black hole with the mass of 4 million suns. Stars orbit this black hole at incredible speeds, some completing their orbits in just a few years despite being light weeks from the black hole. The Event Horizon Telescope has actually imaged the glowing accretion disk around this black hole, showing the shadow of the event horizon itself, a boundary in space beyond which nothing can escape. We pull back further, seeing our galaxy from outside, a beautiful spiral of several 100 billion stars, about 100,000 light-years across but only about 1,000 light-years thick in the disk. Dark matter extends far beyond the visible stars, creating a roughly spherical halo that contains most of the galaxy's mass. Globular clusters, ancient collections of hundreds of thousands of stars, orbit in this halo, some of them nearly as old as the universe itself, witnesses to the galaxy's entire history. Our galaxy is not alone, but part of the Local Group, a collection of over 80 known galaxies dominated by the Milky Way and Andromeda, which is slightly larger than our galaxy and approaching us at about 70 miles per second. In about 4 billion years, these two galaxies will collide and merge, their stars unlikely to collide due to the vast spaces between them, but their structures completely reorganized, eventually forming a giant elliptical galaxy. The collision will trigger new waves of star formation as gas clouds collide and compress, a cosmic catastrophe that's also an act of creation. Beyond the Local Group, we see other galaxy clusters, some containing thousands of galaxies bound together by gravity, mostly by the gravity of dark matter. Between these clusters stretch vast cosmic voids, regions almost empty of galaxies, some hundreds of millions of light-years across. The largest structures we can see are the filaments of the cosmic web, chains of galaxies and dark matter that connect clusters, forming a vast three-dimensional network that spans the observable universe. As we approach the edge of the observable universe, we're also looking back in time, seeing galaxies as they were billions of years ago when their light began its journey toward us. The most distant galaxies we can see existed when the universe was only a few 100 million years old, small and irregular, not yet organized into the grand spirals and ellipticals we see in the modern universe. Beyond them lies the cosmic microwave background, the wall of light from when the universe first became transparent, the farthest back in time we can see with electromagnetic radiation. But our journey doesn't end at the observable universe's edge. Beyond our cosmic horizon, beyond what we can ever observe even in principle, the universe likely continues, possibly infinitely, containing countless more galaxies, stars, planets, possibly other regions with different physical constants, other versions of reality we can never access. If eternal inflation is correct, our entire observable universe might be just one bubble in an infinite multiverse, each bubble with its own laws of physics, its own constants, its own possibilities for complexity and life. Throughout this journey, from your room to the edge of everything we can observe and beyond, space has been listening in its way, responding to the presence of matter and energy, carrying waves and particles, maintaining fields and forces. Every object we've passed has been in constant communication with its environment through gravity, through electromagnetic radiation, through the exchange of particles. The universe is not a collection of isolated objects, but a vast network of relationships, a cosmic conversation that has been ongoing since the Big Bang and will continue until the universe reaches whatever final state awaits it in the far future. As we prepare to return from this vast journey, to bring our awareness back to the familiar confines of Earth and your resting body, take a moment to appreciate the enormity of what we've traversed. In reality, you haven't moved at all, yet in imagination you've crossed billions of light years, seen structures that dwarf all human comprehension, witnessed processes that unfold over timescales that make human history seem like less than a heartbeat. This capacity to imagine, to project consciousness across cosmic distances and deep time, is perhaps one of the universe's most remarkable achievements, a way for the cosmos to observe itself from countless perspectives, to know itself not just locally but globally, not just in the present but across its entire history. The return journey happens more quickly, space collapsing like a reversed explosion, galaxies rushing past, stars becoming a blur, the solar system expanding around us, Earth growing from a point of light to a sphere to the vast globe that fills our view. We descend through the atmosphere, through clouds and weather, back to the familiar landscape of your region, your neighborhood, your home. Your awareness settles gently back into your body, which has been waiting patiently, breathing steadily, heart beating reliably, maintaining life while consciousness went exploring. But something has changed. Having taken this journey even in imagination, you can never quite see your surroundings the same way again. The walls of your room are no longer barriers but permeable membranes through which cosmic rays pass constantly. The air you breathe connects you to the global atmosphere and through it to space. The gravity you feel connects you to Earth, to the Sun, to the galaxy, to the entire universe. You're not in a small room on a small planet, but in the universe itself, inseparable from it, a temporary but meaningful pattern in the cosmic flow.